Last class we looked at very generic methods, penalty function and augmented Lagrangian, feasible directions. These are very generic approaches. Now let's look at today some very structured algorithm. The one we start with is called linear programming, where every objective function in constraints is a linear function of the variables. Okay. So if you have two variable problem, x1 and x2, like it's shown in this particular plot, and you have a constraint in a linear form, that means it will be a11 x1 plus a12 x2 should be less than equal to b1, right? So when you say they are linear, they will be of that form. So in this particular sketch, what I'm showing here is several constraints. So here is one constraint, and this side is feasible. Here is another constraint, and this side is feasible, like that. So you get an overall feasible region, okay, which is shown here shaded. Usually in linear programming, it's assumed that all the variables take non-negative values. So you are always looking at the first quadrant. So these are by default comes in these two axes, and above and right of x2 axis. But then other constraints determine how this will look like. So when you have only linear constraints, you are going to get a convex region, right? It will be a convex region like this. Basically, it's a polygon. It's a region bounded by a polygon. So there will be a lot of corner points that you have, okay, and the inside region which is feasible. So feasible region is the inside region and these lines, okay, on the points on these constraint boundaries. Now the objective function is also linear. So what does it mean? So if I now try to make, so objective function can be c1 x1 plus c2 x2, and say you want to minimize or maximize that. So if I want to plot a contour of the linear function, it will look like a straight line like this. It depends on c1 and c2 values how the slope would be, right? So you have a straight line contour plot of the objective function and a polygonal feasible space. So our sufficiency condition, sufficiency theorem we talked about, gets satisfied because a linear function can be assumed as both convex concave. So it gets satisfied. So the Kuhn-Tucker point of that problem is going to be the optimum. Okay, so that's just for the side information. But now let's try to look at, if I have a linear constraint objective function and a polygonal shape as the feasible region, can a point inside the feasible space be an optimum?
No, sir.
Why not?
Because we can always take two opposite directions. If along one direction the function decreases, it will certainly increase
in the other direction. Yeah, so let's take this for example. Okay, so let's say the function value here is 10 of that contour line. That means any 2 point I take here on this line, the function value will be 10. Okay, that's how they are called a contour line, right? Go down to this line here, which is parallel to that line. It will have a contour line either more than 10 or less than 10, depends on the objective function, the c1, c2 and all that. So let's say this is smaller. So let's say this is 8. Then you expect this to be smaller even, like 6, 4 and 2. So your objective function may be reducing this way. So if you say that here is a point on this line which is optimum, I can immediately argue, so if you are minimizing, I can immediately argue, no, I can find this line which has a smaller function value, and then this line which is smaller function value. So that means you can drag the line all the way before it leaves this feasible space. So this will be then the optimum, the minimum. If I'm doing maximization, then I'm going the other direction. Again, this point will not be maximum because this has a higher value than that, and this has a higher value than that, and eventually this point may become optimum. So it so happens that in linear programming, it's one of the corner point or all the points on a particular constraint boundary here are optimum. The optimum cannot be inside. Is that clear? Is that convincing? Okay, from the geometric point of view? Okay. So now we know in linear programming, it has to be one of the corner points or a segment of the constraint boundary are going to be the optimum points, right? So if that's the case, is there any point for me to search inside? The answer is no. I should not even start from a random point inside like we have been doing and searching within this space, because ultimately I know I have to go to the boundary. Most likely it's one of the corner points. So there are some very smart people early on. They said, if that is so, then why don't we just search along the boundary and not even go inside at all? So I have a much reduced search space, right? Okay, and then I will be able to find the optima very quickly. There are even smarter people. They said, well, most likely corner points happen to be the optima because it's very unlikely. So when you will have all these points as an optima? When your contour line, yes, contour line of the objective function is parallel to this. That means the objective function is same as one of the constraint functions. But that's very unlikely to happen, that you have an objective function that is same as the constraint function. Usually objectives or constraints are different. So in that situation, one of the corner points have to be the optimum. So then if one of the corner points have to be the optimum, you can now think of a search methodology that will just hop from one corner point to the other corner point to the other corner point instead of looking at anywhere else. So you don't even look at each and every point on the boundary of that polygon. You can just hop from one corner point to the other corner point. Is that clear? So you see how much reduction in the search space that you are doing by following this principle and by understanding where the optimum can be. So that's why I say this, if you want to study optimization, you have got to have a good knowledge in geometry. You need to be able to visualize some of these things, of what's happening. Then you can come up with much smarter and more efficient algorithms. Then the question is, how do I hop? How do I even find one corner point, and instead of going to any other place, I can move to another corner point? So that's the big question, so which we are going to look at with a particular method called simplex search. Okay, so that's the one we're going to concentrate. This was suggested by a person called Danzig a long time ago. Okay, around 60s. Then this person is an Indian, Kharagpur, but he was working in US for a long time. 1983, he was working on his PhD thesis, and he figured simplex method is excellent if you have variables that are less than like 100,000, 200,000. Even simplex problems are solved with very, very large number of problems, okay, large number of variables. But he realized if you go to millions and tens of millions or hundreds of millions of variables where the search space is much larger, then there are so many corner points that you are going to have, even that search becomes tedious. Okay, so he thought then you are better off searching through insight. You can find shortcuts through insight to get to the respective optimal point, but you don't get the advantage if you have fewer dimensions, because the number of corner points becomes small in fewer dimensions, so you are better off hopping. So his Kharagpur's method, it deviates from hopping the corner points. It does with what is known as an interior point method. Okay, we are not going to talk about his method because that's very involved, and it only comes relevant if you are doing large number of variables. Okay, so we'll concentrate on the simplex search. So let's continue with the Danzig's method. So Danzig's method assumes that you have only equality constraints. Okay, so for example, you have an objective function that is linear in terms of variables, c1x1 plus c2x2 all the way cnxn, where there are n variables, and subject to lots of linear constraints. Okay, obviously the number of constraints that you have, j, should be much less than n. Otherwise you have a very restricted search space. Okay, so you don't have too many corner points. Okay, because all of these constraints have to be satisfied. Okay, so so that's one of the assumptions he has, and then xi has to be greater than or equal to 0. Every variable is non-negative, but if you have a negative variable value you are expecting, you have to do a variable transformation to make it non-negative. Okay, so this is the main framework in which Danzig built his algorithm, but that doesn't mean the Danzig's method cannot be applied to inequality constraint. So we'll talk about how to handle inequality constraint, because that's all we are going to have in most problems. I will first start with less than type inequality constraint, because that's a little easier to handle than the greater than type inequality. So all we have are now constraints that, let me go back, that will say this left hand side here, okay, is less than or equal to b1. This left hand side here is less than or equal to b2, and so on and so forth. Is that clear? So we are trying to handle such constraints, less than or equal to type. All right, but Danzig's method requires you to use equality constraints. So first thing he said we do is we convert inequality constraint into an equality constraint. How will you convert?
Introducing some
Slack variable. Yes, so what you do is add a variable, a new variable. So if you had 10 variable, n is 10, For the first constraint, you introduce the 11th variable, x11. Okay? So because the left hand side has to be less than equal to 0, that means this has to be negative, right? If I add a positive quantity here, the summation will then become 0, right? So by adding a xn plus j variable and ensuring that xn plus j has to be greater than equal to 0, not less than equal to 0, greater than equal to 0, I am ensuring I am converting the inequality into an equality constraints. Okay. So this is the first thing you do. All less than equal to type you convert to equality type by adding one slack variable per constraint. Is that clear? So if you have j constraints, you are adding j more variables. So you had n variables, now you have n plus j. Okay. I'm calling now, so once you have converted that, you have a situation like this again, right? Everything is now equality constraints. The variables here is not just n, it will be n plus j. And the number of constraints remains the same, is j, but number of variables have become n plus j, right? Okay. So we are having this situation. Now, before you proceed with the algorithm, you need to first choose two sets of variables. One set you call a basic variable, the remaining variables are called non-basic variable. Let me explain what is the definition of a basic variable. A basic variable is a variable out of all n plus j variables where it has a coefficient of 1 in one of the constraints and it does not appear even once in any of the other constraints. So like this, x1 appears only here with a coefficient of 1 and it does not appear in any other constraints. So x1 is called the basic variable for or representing the constraint, first constraint number 1. x2 is another basic variable. See, it's coefficient 1, it's not appearing anywhere else, but this constraint makes this x2 variable as a basic because it doesn't appear anywhere else. Similarly, x3 for the third and so on and so forth, xj for the jth variable. So there will be exactly j basic variables when you have j constraints, okay, and n minus j other non-basic variables. So this set of constraints that you have to convert into that form, and this is called a row echelon form. Those of you who have done a matrix algebra course are probably familiar with this term because you are taught how to do this. It's basically row manipulation that you have to do. You multiply one of the rows with some number and subtract it from the other column, other row, and you can make that happen. We'll take an example and you'll see how to make that happen. So once you have made this, each of these variables are called basic, each of these variables are called non-basic. Okay? So this set of equations I have in this slide is exactly the same as this set of equations, except that I've just manipulated them. Okay? But if a solution x1 to xn satisfy all these conditions, it also satisfies all these conditions. So feasibility is intact, all right? But I'm just writing it in a different way. Now that I have written the constraints this way, what could be a solution to this set of equations? Because there are j constraints and j is always less than n, I can assume that all these non-basic variables to be 0. I can assume anything here, right? So I can assume all of them to be 0, then what is the value of x1? b1 dash. Value of x2, b2 dash. Value of xj, bj dash. So now I've got a solution which says x1 is b1 dash, x2 is b2 dash, x3 is b3 dash, so on and so forth, xj as bj dash, and all other variables are 0. That's a complete solution, right? That solution is a feasible solution to this system, right? It satisfies all the constraints. That means it also satisfies these constraints because they're the same set of equivalent set of equations. So that means that's a feasible solution. Okay? It so happens that feasible solution is one of the corner points. The way the whole thing is constructed from less than equal to this equal to by adding slack variables makes those solutions as corner points. Only corner points become feasible to that set. Okay? Now that I've got a feasible solution, I can evaluate the function value and see how good it is. All right. Now, I have chosen these j variables, let's say the first j variables at random, and I said, okay, these are my basic variables. Now, what I can do, I can replace x2 with maybe xj plus 1. So I can make x2 over there and xj plus. So this xj plus 1, coefficient I can make 1, and these are all 0. Now x2 will have some values here. So in that case, I've got x1, x3 up to xj are basic variables, and xj plus 1 is another basic variable. and x2 to xj plus 2 all the way to xn becomes non-basic variable. I can also do that, right? And that will also be another feasible solution, right? So like that, I can take any from here and replace it or exchange with any from this set. So one basic and one non-basic I can replace, and I will get to another corner point. So as many times you do it, you are actually moving from one corner point to the other corner point to the other corner point. Is that clear? So now the question is, when I'm starting with the initial basic feasible solution, which is the next basic feasible solution I should move to? Okay, so that's what's answered by Danzig in a very nice way. Okay, so this is exactly what I am saying here. Two questions to be answered. First question is, which of the non-basic variables I should make basic? And once I've answered that, then which basic variables have to be made non-basic? These are the two questions. If I can answer, I have an algorithm. Okay, so let me answer that the way that he has done. So obviously there are total j times n minus j options, right? Because one of the ways you can choose the basic variable is j, because there are j of them. Once you've chosen that, there are n minus j variables you have to extend. So there are so many corner points that you are going to have. Okay. Now the first question is answered by maximizing the gain in f. So now you have one of the corner points. You have one of these corner points. Let's say this one. Okay. Now you're deciding where to go, whether to go here, 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 or here. Okay. So Danzig said, I'm going to go to one of those points which is going to increase my function value the maximum. And he said, instead of jumping around too much, I'm going to only look at my neighboring corner points, only this one and that one. And of them, which one maximizes my function value more? That means the difference between the function value of here and here and here and here, which one is more? I'm going to move to that one. So that way you get a direction towards the maximum point. And remember that in LP we always maximize. Okay. So that's the principle we are going to use to answer the first question. Once the first question is answered, we identify the non-basic variable. Then we answer the second question by saying, how much can we increase so that everything stays feasible? So we'll look at one at a time. So let's first answer this question: which non-basic variable to be made basic? Remember, at this instance, when I'm doing it, all non-basic variables are 0. So xj plus 1 to xn are all 0. Okay. Now let's say I am trying xq non-basic variable. It's the qth non-basic variable I'm trying. So now that non-basic variable will become basic, right? When I do it, that means its value is no more going to be 0 as soon as you make it basic. So let's say I want to increase it by 1 unit. It was 0 and I want to make it to 1. How will be the change in the function value? How the function value is going to change? So look at the current solution. Current solution, all basic variables is bi dash. We talked about that, right? x1 is b1 dash, x2 is b2 dash. And all non-basic variables are 0. So what is the function value? Function value is sum of ci xi, c1 x1 plus c2 x2. So these are all 0. So only ci times bi dash for the basic variables we will get, and there are j of them. So this is my current function value. Okay. Now I've chosen xq and made it 1. Okay. Let's see how my function value changes. And now that I made xq equal to 1, so let me go back here. So let's say I have done this one now 1. This is, let's say, q, j is equal to q equal to j plus 1, and I want to make this one basic. So its value will become now 1. So if this is 1, what is the value of x1 now? 0. Say it again. b1 dash minus why 1? It's multiplied with a1 dash j plus 1. So this is only 1. So b1 dash minus a1 j plus 1 dash. Agreed? What about x2? b2 dash minus a2 dash j plus 1. Is that right? So if I increase xj plus 1 from 0 to 1, my basic variables are also changing. Okay? So that's what I have written here. b1 bi dash minus ai dash iq. Right? So this becomes my basic variables. xq is 1. So if I compute, but other non-basic variables are all still 0. So if I compute new function value, it will be c1 times b1 dash minus a1q dash plus c2 times b2 dash minus a2q dash and all that for all the basic variables, plus CQ, because CQ was 0, now it has become 1. So CQ for the qth variable, whatever is the coefficient. Others are all 0. So this is my new value. So if I now take the difference, that means what I'm saying is, if I converted xq to be a basic variable, how much will be the gain in my function value? So f new minus f old will be the gain, and I'm calling that as del f, the difference in f for the qth variable to be made non-basic, to be made basic. It will be, if you take the difference, you will see this gets cancelled. You have CQ minus this quantity, this times this. Okay. So this, if I take xqth variable and make it non-basic, this will be the change in the function value. Now you can compute for all basic variables, sorry, all non-basic variables one at a time. Q start from j plus 1, then j plus 2, and all of them, and then you can look for which one is going to have the highest value of that. The one having the highest value, that Q will be the corresponding non-basic variables, right? Okay, so this is the philosophy of choosing the non-basic variable, that we look for these, we compute this for all non-basic variables, and the one having the highest value will become the candidate. Yeah.
How can we be sure that this x, then for non-basic variable which we converts value to 1, after that how can I say that the point that is obtained, that's an optimum point?
No, we'll say that. So I was going to get to that. This is what is written here. So let's say now, it's a good point he's making. How do you know we reach the optimum, right? So what about, let's say, we are currently at a particular point, corner point, and I have chosen all non-basic variables. For all of them, this turns out to be negative or 0. What does it mean? That means we reached a stage where even if we now exchange with any of the non-basic variables, I am not going to have an increase in my function value. What does it mean? I have reached the optima. So that's a criteria for stopping the algorithm, when none of the del fq is positive. Okay. So right time you asked the question, because I was going to say that. Yeah.
So you just said that we will move to the neighboring point.
Yeah. I'm getting to that. How does this become a neighboring point? Yeah. So I'm getting to that. Okay. So now that we answered this question, that we identified the non-basic variables that we have to make basic. The next question is, fine, I've got xq. Now the question is, how much can we increase? I assume there that I go from 0 to 1. Okay. Now, can we really go to 0 to 1, or can we go more than 1? Because if that is going to improve my function value, I should keep going, right, as much as I can. But what happens as soon as you make xq? Remember, this was the formula. I mean, there I have used xq equal to 1. But now if I put any xq, I bring back the xq here. Now I'm saying, how much can I really increase xq? So if I go from 0 to 0.1 to 0.2 to 0.3 all the way, you see what's happening to xj, to the basic variables. They are reducing, because as you are increasing this, assuming this is positive, we are actually getting smaller and smaller. Eventually, one of the xj's will become negative or 0. Then if we try to increase that any further, what's going to happen? That variable will become negative. And that's not allowed, because in simplex, in the linear programming, all variables have to be non-negative. So that is the limit, that how much I can increase xq. So the limit for the jth variable then becomes, when this is equal to 0, it becomes bj dash over aj dash jq, right, when this is equal to 0. So this is the value by which you can increase xq, this value, you can increase xq for the jth basic variable. So I compute this for all other basic variables, for the same non-basic variable, so and find out which each of them, we find out this maximum value that we can increase. So which is the one that we should take? We will now take the minimum of all these values for every basic variable, because that variable will then become negative first, and we don't want any of the variables to become negative. So we actually take the minimum of these, and that's going to tell me that which of the variables, basic variables, is becoming that for the minimum of that. So that becomes the basic to be exchanged with the non-basic, right? Okay. So here is the algorithm again. Choose a basic feasible solution. That means you find a variable that appears only in one of the constraints and not in any other constraint. You need to find j of them like that. and then calculate del FQ for all non-basic variables and choose the one having the maximum value, okay, because that's going to increase the function value the maximum. And then if you find that none of them is is positive, strictly positive, that means you have reached the optimum and you quit. And then use, if this is not so, then you use the minimum ratio rule, which is just this rule that we have discussed for all basic variable, and identify which of them has the minimum, and those two should be exchanged, and then you proceed. Okay. So if you're solving minimization problem, there are a couple of ways you can fix it. First thing you could do is multiply f by minus f and then use the above algorithm, or you could do is choose the one having minimum del FQ, because now you want to go in the negative direction, right? So you see which one has the most negative value of del FQ, because that's going to reduce the function value the maximum. And then your termination criteria has to be changed to saying as soon as you have all of them greater than or equal to 0, then you quit. Okay. So let me take an example to illustrate how this algorithm works. So let's say I've got a function to be maximized. Oops, what happened here? I think this is 3x2. This one is a little crowded here. I have to move this a little bit this side. Okay. Yeah, do we get it back again? Okay, I shouldn't have done that. Now how do I take it out? Okay. Got that back. Why can't it move? Okay. So we've got this problem here, 2x1 plus 3x2, we have to maximize. Okay. Subject to this constraint that x1 is less than or equal to 6, x1 plus 2x2 less than or equal to 10, and both x1 x2 has to be strictly non-negative. All right. So now all of them are inequality constraints. So this one in LP we don't consider as constraints. This is already assumed in the algorithm, right? So you are maximizing. If this was a minimization, you have to first convert it to a maximization problem. Okay. Now, how many variables are there? 2. So n equal to 2. How many constraints? 2. First one, second one. Okay. But now, first thing we need to do is convert these two constraints into equality constraints. So what I do, I add a slack variable x3 for the first constraint, and I say x1 plus x3 should be 6, and then I add another slack variable to the second constraint x4. You don't put the same variable because there could be a different value here that will sum up to make 10 than here. So x4. Okay. So now both of them are equality constraints. So now how many variables and how many constraints we've got? 4 variable, x1 to x4, and 2 constraints. So j has to be always less than n when you finally convert. Okay. Now this is called the tabular method or tabulu method, okay, of simplex search. So what you do to make this table is first write down all the variable names here, x1, x2, x3, x4. On top of it, you write their coefficients from the objective function. So coefficient of x1 is 2, coefficient of x2 is 3, coefficient of x3 is 0, coefficient of x4 is 0. So you write those. This is the coefficient from the objective function. Okay. Now you come this side and write the word basic, because we are going to now declare for every constraint here which is the corresponding basic variable. So for the first constraint, which is the basic variable? x3. Why? Because x3 appears with the coefficient 1 in the first constraint and does not appear in the second constraint. So that's the basic variable for the constraint 1. So that's why I say x3. And immediately what I do, I borrow the coefficient of x3 in the objective function and write it here. So this is copied here. Okay, and then write the constraint with only the coefficients because the variables are here. So coefficient of x1 is 1, I write it here 1. Coefficient of x2 is 0, I write here 0. x3 is 1, I write here 1. x4 is 0, I write here 0. And then I put a line here and write the right hand side, which is 6 over here. So this one actually represents the first constraint. Is it clear? Now go to the second constraint. Which is the basic variable? x4. Because you see this, x4 is not there, x3 is here, x4 is here with the coefficient 1. So I put x4 here, and borrow its coefficient in the objective function, put it here. And then I write the constraints 1, 2, 0, 1, 10. 1, 2, 0, 1, 10. Is that okay? So after I have written that, now the task is to compute del FQ. Remember what was, sorry?
X2 will not be basic because X2 not carrying a constant 1.
But it has a coefficient 2.
Coefficient should be unity.
Unity, yeah. So you could have manipulated, instead of using x4, you could have divided the whole thing by 2, and then it would have been 1 here, and you didn't need x4. But this is a simple 2-variable problem. You can see everything, but typically simplex problems are solved with these number of variables here could be 100,000, and constraints could be 10,000. So you'll not have a chance to manipulate. You just use whatever it is. So you always add a slack variable. Always add a slack variable.
We can take directly slack variables.
Yeah, you can directly take slack variable like the way I've done. Yeah.
But in that case, if you just keep on adding slack variable, will that not like increase computation?
Yeah, but the algorithm is so efficient, it doesn't increase the complexity that much, right? So you can close your eyes and add slack variables. No, not a problem. Slightly increase. There is a complexity estimate. But you see the overall search point is j times n minus j. So if you increase j by 1, you are not increasing the complexity by too much. Okay? So it's kind of j square it goes, but it's not too much.
Is it possible that all the slack variable comes to be a basic variable? Yes.
Usually they are. Usually at the first time when you are doing this. That's the idea. That first you have only one independent slack variable in every constraint, so that becomes the basic variable to start with. That also you can use. No, in that case you cannot add a slack variable. There are other methods, like you add a slack variable and you subtract another slack variable. That's called an artificial variable, and you expect those two to be equal. So there are tricks. Okay, you just keep on increasing.
Then we can convert into row echelon form and do the same thing.
Yeah, but then I said, if you have 10,000 constraint, doing the row echelon form is not easy, right?
No, but if you don't have like slack variables and for only 1 or 2 constraints,
Yeah.
then
You can also, so what he's saying is, first I have all these I put here and I do a row echelon form with those manipulations. You could do that as well. Okay. But I haven't seen anybody complaining that they are not able to add the slack variables, and so it's easy that every inequality you add a slack variable and they become the basic variable to start with. Okay. All right. Now, before I proceed further, before computing even del FQ, let's try to think that this table here, so every table that we'll be using here represents a particular point in my original space. So here is the problem which I forgot to discuss. So here is my x1 axis, here is my x2 axis. First constraint is x1 less than or equal to 6. So on 6 here, I draw a vertical line. Left side is feasible. This is the inclined line, which is that one. And 0, 0, if I take the origin is feasible. That means the left side of this line is feasible. So left side is feasible, left side of this line is feasible, and of course x1, x2 is always non-negative. So I've got this trapezium which is feasible, right? Which is the optimum? Let's try to see which is the optimum. Now I need to do a contour plot of this objective function. So the way to do that is you assume some value here. Let's say if I assume a value 6, this has to be equal to 6. Then x1 it cuts at 3, and x2 it will cut at 2, and I draw the line. So that's the kind of contour of that contour line of the function, where the one it's cutting at 3 and 2, that will have a function value 6. Then if you increase to 12, it will cut at 6 and 4. So like that it goes. So this one has a value of 28, then 18, then 8. So you see that the function values reduce this way if you go parallel to this contour line. So that means since I'm maximizing, I would like to go as much as possible that way before I leave the feasible space. So which is the optimum? This point, right, is the optimum point. That's the last line, 18. If you try to go any further, you don't have any supporting point from the feasible space. Okay. So now that I know the optimum for this problem, let's see whether this method can get me there. But first of all, where is this point here? See, this figure doesn't have x3, x4. x3, x4 are slack variables. It's not there in the original problem. So this is the original problem. I don't have x3, x4. I only have x1, x2. So what is the value of x1 and x2 in this table? Who can tell me that? Why 0?
because they are non-basic.
Because they are non-basic. Every non-basic variable I said will have a value 0. We assume that. And every basic, so what is the value of x3 in this table? 6. And then value of x4 is 10. But value of x1 is 0, x2 is 0 because they are non-basic. So that means this table represents the point 0, 0. Where is that over here? Origin right here. And that's one of the corner points. Right? One of the corner points. So we're starting from there. Usually if you take all slack variables as your basic variable, that's what happens. All x's are 0 and you're starting from the origin. Okay. So this represents the origin. Now we have to move to one of the corner points. So how do we do that? Okay, first step is compute del fq. So when you compute del fq, what is the formula? Is c of this variable, non-basic variable, c minus cb times a. Remember that? I have written it here. C minus cb times a, and we have to go for all the basic variable. This is for summed over all the basic variable. So if you translate this math into a mechanism here, and that's why we do the table, so that I don't have to remember the math, I could still do it, is this minus this times this, minus this times this, whatever is the result you put here. So 2 minus 0 times 1 minus 0 times 1 is going to be 2. 3 minus 0 times 0 minus 0 times 2 is 3. Well, you only have to do this for non-basic variables, and here there are 2 non-basic variables right here. But usually we continue. We don't keep a track here when you are doing manually, which is basic, non-basic. So we just continue to do 0 minus 0 times this minus 0 times this. But what did you expect here? It will be always 0 because these are basic variables, and you are not taking one of the basic variables in this formula. So it is always going to be 0. But instead of paying attention to which are basic and which are non-basic, you just keep doing all of them. Okay. Now that you have done that, del fq, you notice that one of them will be the highest value. So first notice that there are some positive values. That means I have not reached the minima. In this case, maxima. I have to continue with the algorithm. If all of them were 0 or negative, I would have stopped. That was the optimum point. But it is not. Then I take the maximum value, which is 3 in this case. The way to do is, so 3 says, if I take x2 and put it here as a basic, I am going to have the largest increase in my function value, not with x1. Okay? So do that, and now put an arrow here saying this is the x2 I'm going to choose here. Now I have to see which of these 2 basic variable has to be sacrificed. Okay? For that, I have to do the minimum ratio rule. And the minimum ratio rule, remember, was bi dash over corresponding ai. So you come over here, and your bi is 6. For the first basic variable, it is 6 divided by this coefficient. Now that you've got the arrow, we'll be taking these a's. So 6 by 0, infinity, and 10 by 2, 5. So infinity means, okay, if you take x2 as the basic variables, you can keep on increasing it to infinity. It's still not going to make this basic variable negative. Okay, so that's what it means, because it doesn't get affected. So we ignore those things. Anyway, we'll be taking minimum, so infinity will not become the minimum. Now 10 by, so basically you take the minimum of the 2. Now if any occasions you get negative values here, don't take them, because negative means you can keep on increasing, you will never get it to become negative. It will always become positive and positive. So don't consider negatives, don't consider infinites. Rest of the thing you find the minimum. Okay, so you get, in this case we get 5. So 5 means put an arrow here, and now the 2 arrows meet here. That means x2 will go here and x4 will come there. Okay. So let's go to the next table and see. So this was the same table I have reproduced, and I said that this is the point A that represents. The usual customary that I do is you write down the solution in terms of original variable x1 0, x2 0, and mark the point on the graph if you're plotting the graph to say which is that point. Okay. Now I move to the next table. Now that I've identified, so what I'm going to do, I'm going to replace x4 with x2, and immediately I'm going to bring x2's coefficient here, 3, right? Because I changed this, I have to change this also. Okay. Now I have the same thing. Now I have to do the row echelon on this. Okay, so that means since I made x2 here, I have to look at the x2's coefficient here should be 1, and it should not appear anything here. It should be 0 here. Now how do I make this 1? Because this is what I have before I get there, right? So I have to make this 1. How do I make it 1? I divide everything by 2, both left hand side and right hand side. So this will be 0.5, this should be 1, this should be 0, this should be 0.5, and this should be 10 by 2, 5. Fine? Okay. Now let's go and see if this is 0. This is already 0. So I don't have to do anything else because I wanted 1 and 0 here. It's already there now. So I can bring as it is from here to there. Now you see x2 has a coefficient 1 and 0 here. x3 has a coefficient 1 and 0 here. So they are in row echelon form. Okay. And now I can start looking at del FQ and the point first of all. So what is the point? What is the value of x1? It's not one of the basic, so it is 0. What is the value of x2? It's basic. So value, x2's value is 5. So I have got the point 0, 5. Where is that? 0, 5 is this point. Okay. So that means from this point I move to that one. Let's try to look at del FQ. It will be 2 minus this times this minus this times this. Now I've got 2 minus 0 minus 1.5. So 2 minus 1.5 is 0.5. Then 3 minus 0 minus 3, 0. And all that you do, we still see that one of them is still positive, right? So we have to take that. So we take this row. So x1 has to come here now. And now we go and see which of the two has to be sacrificed. So I compute 6 by 1, 6. And 5 by 0.5, 10. So out of 6 and 10, 6 is the smallest. So x1 will replace x3. Okay. Let's now take a point and see why did it move to this, why not this? Because this is also one of the neighboring points, right? Why did it move to that one? Let's compute the function. What is the function value here? It is 0 and 5, and the thing is 2 plus 3, right? So the function is 2 times, so it is so 2 times 0 plus 3 times 5, 15. And if you had moved here, it would be 12. 6, 0, it will be 12. So this has a higher function value, and that's what is denoted by this. And that's why it moves these things. Okay. So now we've got that. Okay. By the way, getting back to your question about why does it move to the neighboring. Okay, you see at every table here, okay, from this to this, how many changes are we making in the basic variable? 1. So in this case, for example, one of them can enter into the basic. That means both of them are 0. Now one of them has become non-zero. The other still remains as 0. When that happens, you can only move one step. You cannot just move here to there, because if you move here to there, two of them have to be changed, and we are not doing that. But you can come up with one algorithm as well that you say, I'm going to make multiple moves now, not one. This was simplex. This was Danzig's idea. Okay? But you can change number of them can move here simultaneously. That will be your algorithm. And if you can come up with a very nice way of doing it, you can have a very good algorithm. I'm sure people have thought about it. Maybe they haven't found anything good. But that doesn't mean there is not such an algorithm. So going to the neighbor is not the main thing. Okay, but the way he did it ensures that it goes to the neighbor, because one change only happens at a time. But you can jump around in a systematic manner if you want to, and this requires some thought, maybe some analysis and thought. Maybe there's a nice idea somewhere there waiting, and these kinds of algorithms are so popular that if you can come up with a better method than simplex method, immediately you'll be famous. Kormaker were famous just instantly after having that methodology. Okay, it's all about being famous, right? Everything we are doing here. So we get this point B now by this method. Now, have you reached the optimum? Have you reached the maximum? No. We still have 0.5 here. Okay, so that means we still haven't reached. We need to go for one more. So what we decided is that x1 will come here. So when x1 comes here, I also have to bring 2 with it over here. And I have to make this one 1. This is already 1. Now I have to make this one 0. But that's not 0. So how can I make this 0?
Subtract the first row from the after multiplying the second row by 2.
No. Wait a second. Am I saying it right? No or yes? So which is the pivoting row? You have to see that. Which is the pivoting? Which one you want to make 0? This row. So this is not your pivot row. Your pivot row is the x1 row that we're bringing in. So you have to multiply a number there and then subtract from here. You would get the same answer, but you have to follow an algorithm. And that is that if you had a third constraint, you still do the same thing, that you multiply this by the number which will make this third one 0 here. Okay, so this is the pivot row. So I will multiply this by 0.5 and subtract from here. So 0.5 minus 0.5 times 1, which will be 0 now over there. 0 will be here. And then same thing I do here. 1 minus 0.5 times 0, it will be 1 here. 0 minus 0.5 times 1, it will be minus 0.5 here. And 0.5 minus 0.5 times 0 will be 0.5 here. And 5 minus 0.5 times 6 will be 3 over there. And this is what, I'm sorry, 2 there. 2 there, yeah. So this is what I get here. Okay, now you see x1 is in row echelon form, so is x2. x1 I brought 2 over here, and this remains. Now let's find out which is this point. So what is the value of x1 and x2? x1 is 6, x2 is 2, and that is that point now. Okay, and let's compute del fq. Again, 2 minus 2 times 1 minus 3 times 0, 0, 3 minus that, and all these. Now you see nobody is positive here. So we have reached the optima. So you'll quit, and we knew that that was the optima, right? So starting from the origin, it follows the quickest path. Not I won't say quickest, but the one that's going to increase the function value the most. It follows that path by the simplex method and takes you to the maximum point in a very fast manner. So adding another constraint or variable or anything is not a big deal here. It's really very, very quick. So in 3 iterations we get here. Yeah.
So will this algorithm always lead to the optimal solution, the minimum number of iterations? I mean, it seems quite clear.
With this principle, yes. But as I said, if you change multiple, so if I had the liberty to change both x1, x2, then I could have eliminated this step. I could have had x1 here and x2 there. And that would be just one step I'm going there. But I don't have that algorithm yet. This algorithm, yes, this is going to go in a minimum number of steps. Okay, one change at a time. Okay.
Computational complexity of this seems to be number variable.
I take it back. Actually, it may not be the minimum number of steps, but because if you have, it's still not a nonlinear function, but I don't know what happens in higher dimensions, because it could be that if you have a higher dimension, let's say 3 dimensions. In 2 dimensions, we have 2 corner points adjacent. If I have 3 dimensions, I can have 3. If n dimensions, I can have many, right? So now this method is going to choose the one that's having the maximum increase in the function value. But that may be far away from where the optimum is, because from there on, there may be very slow changes. But if you have gone the other way, which is not the highest increase, maybe in one step you would have gotten, because the function value changing is such that that gives you a shortcut. So I'm not 100% sure that it takes the minimum number of steps, but it's an algorithm that works, that will eventually take you for sure. Okay. Yeah. What was the follow-up question?
Like computational complexity of this
is j times n minus j, maximum that many points you have to do, right? Any other question?
You have more than one optimum point.
You can have infinite points. Like what if your objective function is identical to the constraint, then any. So it's going to only find one of the corner points. The first corner point it comes across. It will not going to find anything intermediate. This algorithm doesn't have that power. Okay, but it is one of the optimum solutions. Any other questions? These are good questions. Okay, so hopefully it's clear, right? How to do, and you'll have an exercise problem to do in the afternoon. Okay. Now let's go to greater than equal to constraints. What do we do when you have greater than equal to? Okay, we could do the same thing. We can add now we can have a slack variable. Now we have to subtract it, because this is supposed to be bigger than 0 or equal to 0. So if I subtract something, it will come down to 0. And make sure x n plus j is also non-negative. But by adding this, like the slack variable when I added, it gave me the initial basic variable as well, right? But by subtracting this, does it give me the initial basic variable? What's the coefficient of this variable? -1. But I said it has to be +1. Right? So it doesn't give me that freedom. So to make another slack variable, to make a basic variable, what they do, they add another artificial variable. So 2 variables are introduced to take care of one greater than type inequality constraints, if you want to do it manually. Or if you want to do it algorithmically, but the algorithms are such they don't ask you to do it this way, they just do it internally. But you need to basically add another variable which is a different name. It's not called the slack variable anymore. It's called the artificial variable, because artificial you are adding to get the initial basic feasible solution. And your slack variable is still that same. Yeah? No. Why can't we do that? That's a good question again. Why can't we do that? What if we multiply by -1? You have to multiply the right hand side. So what happens to B? No, that's what he's saying. Multiply by -1, convert it to a less than equal to constraint, and then add a slack variable. But what happens to the B? Become negative. And what did I tell you? That every basic variable takes the value B. So x1 will be minus something, and that's not allowed. Every x1 has to be greater than equal to 0. So all your B's have to be positive all the time. So you can't do that. Although theoretically you think you can do, but the whole structure of linear programming, the way it works, is such that you can never have B's negative, and that's why you can't do that process. Yeah.
If the given condition minus B1 means then we have to multiply overall -1.
How many times you're going to multiply by -1? You did once by -1 so that you can handle inequality, less than to greater than to less than, and now you got a -1. If you multiply, then you have changed it to greater than equal to sign again. So you're back to the problem that you have a -1 coefficient here, right? Yeah.
So why is it not permitted that the variables have negative values?
That's how the whole thing is designed, right? This minimum basic ratio rule. That's what you're saying, is that we are going to choose an xq such that xj just becomes 0. If you start increasing xq, this is reducing, but as soon as it hits 0, any further increase here is going to make it negative, and we don't allow that. So this is part of the algorithm, that every variable has to be greater than equal to 0. If you don't allow that, you don't know which basic variable to choose. You have no algorithm. So just to have that, he has to assume that everything is greater than equal to 0. Okay, and that is also true in solving most practical problems, because x's are dimensions, number of quantities, and so on and so forth. They are never negative. Okay. Any other question? Okay, so let's continue with the dual phase method. So now we've got this additional artificial variable set in addition to slack variable. All of them have to be greater than equal to 0. That's all right. So now there are two phases you have to use. In the first phase, you try to find a basic initial feasible solution. So what you do, you forget the original objective function that you have to maximize, and you minimize the sum of all the artificial variables, so that all artificial variable goes to 0. And then once you get that, you have a basic feasible solution to start with, then you reintroduce the objective function. So these are two phases. Let me explain with an example. So it's the same problem, except that I have now added a greater than equal to constraints. Let me see if I have a sketch. Yeah. So remember this problem, right? Now I've added this new constraint, and I said it's greater than equal to 0. So 0, 0 is no more feasible. When we do the basic feasible solution, remember we started with 0, 0, but now that's not feasible anymore, so I can't use that. So to find a basic feasible solution, it has to be either this or that. So how do we find that? That is done in the first phase. So let me get back, first phase. Yeah, here. Okay, so do the same thing again. Slack variable for x1 by x3, slack variable of this one by x4, slack variable minus x5 because it's greater than, and then I add an artificial variable x6 and make it equal to 2. So everything is equality now. So x6 is the only artificial variable here. So if there are 5 greater than equal to, there will be 5 artificial variables. Okay. In the first phase, we don't consider our original objective function at all. We say I'm going to minimize x6 or maximize minus x6. The same thing, because LP does maximization. That's why I converted the minimization to maximization. Here coefficients can be negative. It's not a problem, but these cannot be negative. All right, these cannot be negative. So I do that first. If I had another greater than equal to, I would have had x7 or x8. If that was x8, then x6 plus x8 is what I'm going to be minimizing, or minus x6 minus x8 is what I'm going to do. Okay, so now to solve this problem, I go back again. There are 6 variables, 3 constraints. Okay, n equal to 6, j equal to 3, So I write all 6 variables, their coefficient in this objective function. See, I'm not considering that anymore in the first phase. So they are all 0 except the x6, which is -1. What are the basic variables? x3, x4, and x6, right? So x3, x4, and x6 coming from the respective equations. I write the equations with the right hand side, and then I compute del fq. 0 minus this times this, minus this times this, minus this times this, 1, and you see that there are 2 of them having the same value. When this happens, you can choose one at random. Okay. So in this case, I may have chosen which one comes here, x2. I may have chosen that one, yeah, at random. So now you go to this side and do the 6 by 0, 10 by 2, 2 by 1, and I see 2 by 1 is the minimum. So that means x6 will be replaced by x2, and I get it here. All the coefficients come over here, and I now have to make x2 1 here, 0 here, and 0 here. So 1 I have already got, so I can write the whole thing here. In order to make this 0, what I should do now? I should multiply this one by 2 and subtract from the second row. So 1 minus 2 times 1 will be -1. 2 minus 2 times 1 will be 0. 0 minus 0. 1 minus 0. So 1. So like that, you do 10 minus 2 times 2, right? Be 6. So like that. Third one is already 0 here, so I don't have to do anything. I just bring the whole thing over here. Okay. Now compute the del fq. Everything is 0 or negative. So that means I've reached the optimum of this function. Now that means that I have got a combination of x1 to x5 where there are initial basic feasible solutions. So I can now forget x6 and look at this now. What are the basic variable? x3, x4, x2. So x3 I have 1 and nothing else. x4 I have got 1 and nothing else. x2 I have got 1 and nothing else. Now I have got x2, x3, and x4 as a basic feasible solution. So I can forget this problem and I can get back to my original problem, because I had difficulty getting that to start with to solve this problem. So this first phase helped me get that. So now I don't need x6 anymore. So I will have a problem just up to here, and I have got, so it basically what it did from here to there is manipulated these equations so that x2 has become alone here without appearing in any other 2 equations. And already I have x3 and x4 from the other 2. Okay, is that clear? So now we move to the original problem. So this I will only keep this much. I will forget x6 now. So here is that same table. Okay, and now my objective function has come back. The original objective function. It is no more 0, 0, 0. It's 2 and 3 here. So I do 3 for 2 here, and now recompute del fq, because this is already in row echelon form. I compute del fq, 2 minus 0 times this and this, and now you see there is 1 that is still positive. So I do the minimum ratio rule. I see this x4 has to be replaced with x5. So it goes over there, and I still see that this is 0.5. So I do one more time, and now I see everything is negative or 0, so I have terminated. If you look at what's happening in this plot, which point is this? What is x1 and x2? x1 is 0. What is x2? x2 is 2. So I'm starting with this point, 0, 2. Okay. What is x1, x2 here? x1 is still 0. x2 is now 5. So it is moved here now. And what is this table? x1 is 6. x2 is 2. So I've moved here. So started from here. So my first phase allowed me to go from here to there. And then I started with my original function. Then I moved from here to there, then there. Okay. So because of the addition of these constraints, I had an additional stage, additional step. So when you have greater than equal to constraints, it's a bit more complex to solve the LP problem. If all are less than equal to, you have an initial starting point, and it's a little quicker. Yeah.
The purpose of that x6 value.
So x6 was artificiality. Right? I had to add x6 because I don't have a starting initial basic feasible solution, right? So I said, okay, I know that x6 has to be greater than equal to 0. Now if I say I want to minimize x6, and x6 has a constraint, x is greater than equal to 0, so what is the minimum value that you can expect? It's a variable that you want to minimize, but it has to be greater than equal to 0. So what is the value that you can get? 0. So as soon as I get a value of x6 equal to 0, it's as if saying you don't need x6, because its value is 0, so I can take it out. Because it's appearing only here, I can take it out. but I did not have that in the initial basic feasible. So I am using a LP to give me that solution for which x6 is 0. So here it converged means I have got the optima of this problem, and optima of this problem I know when x is equal to 0. So now that I have got the x6 0, I do not need it anymore, and I can now take the remaining ones and start my original problem. Okay.
So it is only used for conversion process.
Yeah, it is only used to find the initial basic feasible solution, like this solution here, which I could not find from my equations. If I manipulate, I can do, but as I said, when you have 10,000 constraints, you will not be able to manipulate and get that. You need such an algorithm to give you that initial starting point. No, we're just changing the objective function in the first phase, which is maximizing minus of sum of all the artificial variables. Once we get the optimum of that, we know each and every artificial variable has gone to 0 now. So I can start my original function. So we take out that objective function and put the new objective function and continue from there. Okay. Any other question? All right. So I think it's a time to give a break, tea break, and then we'll start after coming back. 5 minutes, okay?
This one we have got the minimum. Why we are making other this Basel 1 or 0 mostly? I'm forgot to the.
Okay, so you have not understood anything I said, because the definition of the basic variable is that it has to be 1,
Okay.
and rest all has to be 0. Otherwise, it's
Okay.
not a basic variable.
Okay, that has to be 0. Okay.
Has to be 0. That is the definition. Okay.
So one thing here we have added and we have subtracted x5. Where is that? We have subtracted x5 to make it less than
To make it equal to 0.
to make
Because this one has to be greater than equal to 2, right? So if I subtract something from it, then only it will become equal to 2.
then it will be equal
So
to
that's why I have subtracted x5 and made sure x5 is positive or 0.
okay.
But then in doing so, I cannot say x5 is a basic variable because its coefficient is -1. I need a +1.
+1.
So I don't have a basic feasible solution. That's why I'm adding another artificial variable so that I have a basic feasible solution.
This is as it is +1.
Yes,
So we are
that's right.
assuming it as
Yeah, so we are always adding this. So it immediately gives me 1 as the coefficient. But I don't want x6. So that's why I do this initial step phase 1 here to find a solution for which x6 will turn out to be 0.
0.
As soon as I get x6 equal to 0,
Then we remove
I just remove it. Yeah.
Sir, I was actually trying to improve this algorithm.
Mm-hmm.
So what I thought said it actually what this does actually it will so this is actually g1 x plus 1 minus square minus gx square.
No. You want to do square here. The way it is done is not square individually. You get the bracket value of that and then square it.
I was thinking to use an exponential function instead, because if you look at the graph,
For
the
what?
higher values
Which is the
for
exponential?
this function,
Uh-huh.
I was thinking to use the sum of squared error of this value, like gx
Okay.
plus 1 minus gx square.
Mm-hmm.
So if you see the exponential function at higher values, it will have high value.
Yeah.
Value will exponentially increase, but whereas low value, the value
So
will.
what is over here? You have x-axis.
Yes, sir. Exactly.
What is the x? Is it x or gx?
So this This will be this whole term, gx plus 1
Oh,
minus gx.
the x-axis is the whole term.
Yes, sir.
Difference.
Yes, sir. Because
I don't know
you
what's
told
that
me
going to achieve.
You told me that we.
So here is 0.
Yes, sir.
So do you want gx to be more than gx or less than gx? So these ones, when gx plus
Because
1 is
when
more.
we reach gx plus 1, we are actually violating the constant less. I mean, we are, as you told me in this figure, we are improving the value.
Yeah, you are reducing the value.
Reducing the value.
Yeah.
So this whole term will decrease as we do more iterations. So this will come down.
Okay. So this is not this
follow
method you
smooth
are saying.
path
You are talking about improving this method, penalty function method,
Yes, sir. Yeah.
not
Yes, sir.
not the augmented Lagrangian
Yes, sir.
method. Yeah, you could do various things. You could have you don't need this just straight line. You could do exponential. You could do polynomial. Yeah. You could do. But I think the whole philosophy still remains the same. You still need to adjust the R. That is the problem with this
And
method.
sir, what if we use different R values for different constraints?
Yeah,
But it
you
will-
can use, but then you have more
yes,
parameters
sir.
to update.
Parameters.
To avoid that, I say we normalize and we have just 1 R. Yeah, 1 R to fiddle with. But I will talk more about this when I get to multi-objective. There is a much nicer way you can get the value of R. You can actually get a knowledge of what would be a good R
Yes, sir.
straight away, and we have exploited that, and we have much better performance than any of these methods. So we'll wait till that point. It'll probably come next week, not tomorrow. Okay, but these are kind of building up the ideas and concepts of classical optimization, which I think all of you should know before you know genetic algorithms or any advanced methods. Okay. Which one again? Has to be, otherwise you don't have a region. So if say for example you have a 2 variable problem and you have two equality constraints. So one constraint is a line. It's an equality constraint. So it's a straight line. Every point has to fall on that line in a 2-dimensional space. You have another constraint. Every point has to fall onto that line. So every point has to fall on both the lines. How many points are there? Just one. Right? So if there's only one feasible point, that has to be the maxima, minima, whatever you call it. So there is not much to search over there. So if j is equal to n and you have 2-dimensional space and you have 2 straight line equations as constraints, equality constraints, you have only one feasible point. That's not a search space, right? So but when you have, so you need at least one less. If you have 2 variable and 1 constraints, now you have all the points on that line is feasible. So now there is a search space. You can go and search. If you have exactly equal, then there's only one point, right? So that's why I said that j has to be smaller than n in order for you to have a search space so you can search within it. And then, so when you have 2 variables and 2 inequality constraints now, so as soon as you have one inequality constraints, I am adding another variable. So it's no more a 2 variable problem, it's a 3 variable problem and 1 equation. Now you can go, if you have another equation, then you have 4 variables because another slack variable comes in and 2 constraints. So now it's a 4-dimensional space with 2 constraints. Now you have this kind of polygonal shape that you have there. You see? Yeah. Okay, we are back up on. So now what I'm going to do is demonstrate to you the Matlab and how linear programming can be solved. I mean, in the afternoon today, you are going to be solving by hand this tabular method. Okay, but later on, we'll see next week if you have the access to the Matlab downstairs. I will give you some assignments for that, or you can try it at home later on. So, how many of you know Matlab or have used Matlab? Okay, a little more than half. But let me just make a very quick introduction to Matlab before I show you the linear programming thing. So it's actually a matrix processing software. Everything in Matlab is done using matrices. Okay, it turns out that a lot of things you can think that way, and anytime you have an array, you can consider it as a matrix of one-dimensional matrix, and you can do stuff. The other nice thing in Matlab is that most of the algebraic manipulations that we have to do are already stored as a macro. For example, if you want to find eigenvalue, all you have to say EIG and give in bracket the matrix. It just gives you the eigenvalue. If you have to solve a set of simultaneous set of equations, it can find it. There are so many things it can do. So many people, ordinary differential equation solvers and stuff like that. A lot of macros are there. There are some optimization softwares as well, which we are probably not going to look at except the linear programming and quadratic programming stuff. But there are some nonlinear programming codes as well. In fact, there are genetic algorithms coded as well. So it's really a good tool to know. In advanced studies, advanced research, I think this is absolutely essential according to me. So if you don't know it, spend some time. You don't need too much time to learn it, but just know it and try to use it. So when you, okay, instead of showing it there, I have a Matlab opened up here. Let me see if I can, yeah, no, not that. What if I do this? Yes. So this is how the Matlab window comes up when you open. You can open files if you have already saved files. If you want to do a new one, you can start from here. But this is called the command window. Okay, a lot of things you can do here. For example, a vector can be represented this way: a equal to, you always do it the square bracket. Let's say 1 and blank 2. And if you don't put a semicolon at the end, if you press enter, it actually shows you what it read. So it says a 1 and 2 means it's a row vector having the first element 1, second element 2. If you want to do, you can say a transpose. Transpose is just with a dash, and then it converts into a column vector. Okay. Then if you say C equal to A times B, what do you expect? Product. So will it going to be a scalar or a scalar? Because I am multiplying a 1 by 2 vector with a 2 by 1 vector, so you'll get 1 by 1. See what happens. It gives you that. But what if I did D equal to B times A? It will be 2 by 2 matrix. So you get the 2 by 2 matrix. So it's just these operations, all that. If you want to do the eigenvalue of D, you just say ig, enter. It gives you the 2 eigenvalues. Now remember how much time it took for you to compute the eigenvalue. If you go to Matlab, put those matrices and just gives you the eigenvalue and see if they are both positive or not, to see if this minima and all that. Okay. So it's a very handy tool to have to do. So there are a lot of other things you could do with it. A matrix can be directly represented. Like if I say F is a matrix, let's say I do a 3 by 2 matrix. So I do 1, 2, 3. So that's the first row. Then I put a semicolon. That brings me to the second row, and I have to do, let's say, 3, 4, minus 1. And I put enter, and I get the 2 by 3 matrix. If I had done the same thing with a semicolon at the end, it will accept it, but it will not show it. Okay, but it accepts it as a, and you can go here in this F, and it's stored in this workspace. It shows that there is a F, and it shows the size and everything over here, all the elements and everything it shows. Okay. All right. So okay, so there are much more stuff, and you can go over here with the documentation. You can write anything here, and it opens up another window, and it shows you what is the syntax, and there are some examples. So you need to spend about an hour, and you can become an expert with Matlab. Okay, it's not a very big deal here. Okay, now I'm going to show you another thing. So this is, everything is done on the command window, Now, sometimes when you do command window, nothing is getting saved. Okay, but there is a way to save all that stuff. Also, if you do save MATLAB work, it will show you how to do. But you can actually open or maybe a new script. If you go to new script, another window splits up here. It's called editor. Now the same thing I could do. So for example, I can copy this. Let me copy some of the thing from here that I have done. So say I copy this and put it here. So this is a kind of editor, and I don't want to see it every time, so I'm going to do it this way. First thing I did is that, and then I did B equal to A inverse A transpose. So I do that here. Did I copy? Copy, come over here, save it, put a semicolon everywhere, so I don't want it to output that. And let's say I'm going to do this one straight away. Copy, I get the D, and then I'm going to do E equal to I of D. Okay. This time I want to print this, for example. So I say I don't put the semicolon. So I want to see what is the eigenvalue of this matrix. Is that okay? All right. So now, once I've gotten that, I can go there and run. So let me clear this part here so that I'm not confused. Sorry, not there. Here. Clear. So now everything is gone from the memory here. So now I go there and put run. First, it will ask you to save that file so that you don't lose it. So I save it somewhere. Let's say in my original directory here, I save it as test.test, and it will always put it as a .m extension. So let me put test KGP, and it will put that. Okay, let it put it here. Save. Now it says it was in a MATLAB directory where the MATLAB is stored. Now it says, do you like to change it to this directory where you saved your file? You say yes, change folder. And then not only does that, it runs and gives you the result. So this was the eigenvalues, right? We got 0 and 5. It's not writing, so test KGP, and it's not writing any other because I didn't ask it to write. But if I just do, let's say this one, and I run it again, so now D and E will be printed. So I do run again, and now you see what I have. Test KGP, first it runs D, tells you the D, and then it tells you the eigenvalue. Okay, so now this is saved in here, so you can come back anytime later and redo or change anything here. So this is like an editor. Run command will solve it over here. Is that clear? Now we're going to go graduate to already to solving linear programming using this MATLAB. Okay, so I put here linear programming. I already see some linear, but that's not what I want to do. Linear programming. So it says linprog is the command. So let me click it, and I want to see the syntax. So here is the syntax. It says this linprog here routine can solve this problem. Minimize x minimize the variable with respect to variable x. This function f transpose x. What does it mean? F has to be a vector. F is a vector. So f1, f2, f3 all the way. So it's f1, x1, x is also a vector. So f1, x1 plus f2, x2. I call this c, c1, x1 plus c2, x2. So you need to supply the f vector, and such that a dot x less than equal to b. So now A is a matrix. So this whole thing I talked about, a11 x1 plus a12 x2, all the equations together, inequality type, I can put it as a multiplied by the x vector is less than equal to b vector. So all of the constraints can be represented this way. I can also do equality constraint, because somebody asked me what if there is an equality constraint, right? I can also give a set of equality constraints here. I can also specify now, it doesn't have to be 0 lower bound, because I said you can do a variable transformation. So MATLAB's code here already put everything into it and made it more general. As soon as you put LB here not 0, let's say LB is minus 5. So you want minus 5 to plus 5. This code can handle it. All it does is it transforms x1 to a y1 where it adds 5 to it so that you always get to 0. So all these are done internally. Okay, manually you have to do all that if you have to have a different lower bound, but it can go up to lower bound, upper bound. Upper bound it handles as a greater than equality constraint now, and it goes through the dual phase and everything, but it's not telling you all that. It just allows you to give everything the way you are used to, like in any other optimization problem, and it internally takes care of so many things. Okay, and which you have learned today how it does internally, and that is, I think, to me is very important if you're taking an optimization course, because anybody else who has not taken the course can also use this code, and they would never know what goes inside the code. Okay, but you know the greater than equal to and less than equal to, how much difficult it is to satisfy, right? So these are very important things to know before you use any code. Now there are several syntaxes you have here. Simple would be just supply f, a and b, and that's what we've been doing in that. We don't have an equality constraint we gave, right? We didn't give any bounds here. So if you don't give any bounds, the default is greater than equal to 0. Okay? So just this will be the bare minimum you need to run the linprog. You have to have a cost function, f1, f2, all that. You have to have at least some constraints, and x greater than equal to 0, that is default. Okay? Now you can start making it more and more complex. If you have some equality constraints, you have to give this matrix and this vector here. If you want to supply lower bound, upper bound, you can give it. If you want to say that you want to start with a particular point, because you don't want to start with the initial basic feasible solution. So it can start from if you know a good solution already, you can start from there. So the overall time will be saved. Options allows you to do much more things, controlling of various things. So there are more details that we'll find over here. Then there are other flexibilities. At the output, you can simply get the final solution, the x star, or you can get the final solution and the corresponding function value, or did it really properly exit? That means it is terminated with proper termination conditions, so that you can accept the solution that you have, and several other outputs. And we hardly use these things, but there are a lot of options that is adding. Everything is described here, and also, so every one of them is described here. Also, there are some examples of how to input stuff. So how the A should be inputted, B, and some results that you get out of all that. So it's, if you read this through this drop down menu, you actually get a pretty good idea of how to use it. Okay, so we'll go back to our MATLAB space and try to solve the same problem. Okay, so now do you pass me one of these books so that I can see? I have it on my slide, but I don't want to move to my slide now and adjust this. So, okay, let's say I'm going to solve the same problem. First let's solve the less than equal to sign. So let's go to page, let me see if I have it here, linear programming. Yeah, it's 47. Yeah, 47, the lower slide, the left lower slide we are looking at, right? So minimize 2x1 plus 3x2, the problem we just solved, the first time we solved. And then x1 less than equal to 6, x1 plus 2x2 less than equal to 10, okay? So now tell me, what is my f? So I'm going to create another file, okay? Now I'm going to go to a new one, script. So I'm going to go to, so what is my f vector? I need to supply f vector in this. 2 and 3. Is that okay? What is my A matrix? Okay, so what is A? A means the coefficient of x1 and x2 in the first constraint. That will be the first row of A. What is that? 1, 0. Then I put a semicolon to go to the next constraint. 1, 2. Good. You always give a blank. Okay. So that's the A. What else do I need? I need B, the right hand side. What is the right hand side? It's a vector 6 and 10. 6, 10. You could also give a comma, 6, 10. That also works. Okay. That's all I need. So
Should not be a column vector, sir.
doesn't matter. You can give a column vector. MATLAB is smart that way. If it's just a vector, it knows what vector it's looking for. Okay, but if you do manipulation, like multiplying and all, then you got to be syntactically correct. But using these things, it doesn't matter. We can try. I mean, we can see what happens. So let's say I'm going to do x, function value. Okay, so I want the optimal solution and its function value. I call linprog, and then the syntax was I give f first, then A, then B. Okay, that's it. And I'm not going to give a semicolon, then it's not going to give me x and xv. Yes, good point. It will be minus f, because it is a maximization problem, but linprog minimizes. right? We would have otherwise gotten a wrong result. Okay, so now let me run it. If I run it, it's going to ask me to save it. I'm going to save it now in a proper directory because this is my main directory. So let me go and choose IIT KGP, and I have 2016 exercises. Let me put here linear programming 1, and it will already put a .m extension there. Okay, change folder to that one, and it has already solved it and give me the solution 6,2. Remember the solution 6,2 we had? And now it gave me minus 18, but that was plus 18, right? Because I put a minus f, yes, it gets the minimum value, so you have to make it plus to get the actual value. Is that okay? So it was piece of cake for it, right? Okay, now let's do the equality constraint. So now we move to the again page 13, but top right one. So there is an additional constraint I had, x1 plus 2x. Where is that? Oh, sorry, it's oh yeah, this is the bottom left one, x1 plus x2 greater than equal to 2. So how will I change everything? This remains the same. A now will have another one. Okay, so but remember the syntax of the linprog, it says ax less than equal to b. So how do I make that ax less than equal to b? One thing I can try, multiply everything by minus 1. Let's try and see what happens. So colon minus 1 minus 1. Okay, it's getting too much, I think. So let me write down what it is. So I had the constraint which was x1 plus x2 greater than equal to 2, right? So but the Matlab wants you to do ax less than equal to b. So one way I told you before, I could just multiply by minus 1, but then I said this becomes minus, so manually you cannot do it, the manual procedure. But does Matlab have some sophisticated way to take care of it? Let's check. Okay, so let's feed it this way now. So I have fed it minus 1, the coefficient, and I have to add here minus 2. Anything else? Do I need to change? No. Let's run. What is the solution? Again 6. So it handled it. It gave me the right result. So Matlab has internal ways of handling, but actually what it's doing, it's converting into the dual phase problem and solving it. Okay, but we could also maybe do it the dual phase way and get the result. Okay, first you have to have the objective function here, you have to change to only x6, but Matlab you cannot do this because Matlab you are not supplying slack variables and artificial variables. So what is the other way you can use Matlab? Do I have any suggestion here?
Solution of linear.
No, I don't have any other suggestion here. So this is the only way you have to do in MATLAB, because there is no way you can give a greater than equal to in MATLAB. So this is the only way, but it knows that you are maximizing, so it does internally and gives you the right result. Is that clear? Or you are confused?
All these instructions can be given in the command window.
You can also do everything in the command window one by one, but then you don't have a saving of those things. But if you put it here, you are saving it in a file, so for later uses you have that information.
Manipulate over here and you can
Yeah. Anything wrong? For example, if I do something wrong, let's say I don't give this minus 2. Okay, so I gave here 3 rows, but I didn't give 3 rows for B, 3 elements for B. So let's see what it does. It will say there is an error. Okay, so it says the number of rows in A must be the same as the number of elements of B. It's quite smart. It tells you where the problem is, and you can go there and realize, you forgot to give minus 2 here. So everything is saved in one place, then you go and put minus 2 and run again, and now everything is fine, it gives you the result. Okay. So unless it is syntactically correct, it will not solve it, right? It will not be able to solve it. So, and it will keep on pointing you the errors till you correct it. Okay. All right. Now, as I said, it is much more robust. You could actually do equality sign and everything, all those things. Okay, so I'll come back to MATLAB later. Let's now go back to the slide again. Okay. All right, so I need to see the slide here. Okay. So I've already talked to you about some of these. There's equation solver and all that I talked about by doing inverse and all that stuff. Okay, these are the things I just talked about. Okay, this is the generic linprog routine which I have showed you. This is another big problem I solved. 5 variable, 2 inequality, 2 equality, and you can see how it works. Here there is some equality constraints, there is inequality constraints which I am solving. I am giving some lower bound, and here is the result that I get. And this problem I got from a paper where they have given the solution by some other way, and I just wanted to match if Matlab does it. So it seems to have found it the correct answer. Let's move to now quadratic programming, which is another structured algorithm. Here the objective function can be quadratic to the functions, to the variables, but all constraints have to be linear. Okay, so you have all linear constraints, so you have still that kind of a polygonal shape as feasible, but now your objective function can be quadratic, like a sphere or whatever, parabola or something like that. Now can an insight point be optimum? Like before the linear programming we said no, insight point cannot be optimum. It has to be, the optimum has to be one of the corner points. Now when I'm doing quadratic programming where the objective function is quadratic function of the variables, can an insight point be an optimum? It can be, right? Okay, so that means I need to change the whole philosophy. It is no more linear programming. Okay, so this kind of problem you're saying, and there are many problems in practice which can be that way. At least if not, you can approximate the objective function as a quadratic by Taylor series expansion and constraints in linear, and then you can solve it. Now, only thing I'm going to say, if you have a quadratic objective function and linear constraints, let's try to think of applying Kuhn-Tucker conditions to this and write down the optimality conditions. What happens in the Kuhn-Tucker conditions? Equilibrium conditions, you have what? You have the derivative of f, you have the derivative of constraints. So if your fx is quadratic, what is the derivative? What order is the derivative? Linear, right? If you take x square, you do a derivative, you get x, right? 2x, which is linear. So when you differentiate a quadratic function, you get a linear. So your equilibrium condition is linear in terms of x, and that's with the equality sign. That becomes a constraint or whatever. All your constraints are linear anyway. The next set of Kuhn-Tucker conditions are constraint satisfaction. So these are again linear. Okay, so we have first one linear, constraints are linear, constraints can be less than equal to, greater than equal to, equality, everything. Now complementary slackness, what is that? U times G. G is linear, but U is linear because it's U, just U, but their product is not linear. So U times G is not linear, and that's a headache to mathematicians, that it is not linear. Okay? But it's just a very simple form. It's actually called a bilinear curve because there are two linear functions as a product together, right? So if you do, okay, so that's the little difficulty, but let's keep it there. And what's the last one? Is that all u's have to be greater than 0. That becomes like a natural variable bound for u. So in this problem, now I've got this quadratic optimization problem, programming problem. I write down its Kuhn-Tucker condition. It seems like everything is linear except that complementary slackness. And my variables there are x, u's, and v's. These all are variable now, but everything is linear except this one little thing. Okay, now they say that this one little problem that we have, we can take a special care in updating my basic to non-basic variable. So you see what it's saying, u times g, g is linear, u is linear, has to be 0. And we said either u is 0 or g is 0. Okay. So now if I see that for a constraint, okay, if g is non-zero, I know that u has to be 0. So if I'm thinking u as a variable and I want to make it a basic variable, I first check if the corresponding constraint violation is positive or not. If it is, non-zero or not. If it is non-zero, I know this has to be 0. U has to be 0. So I will never take u as a basic variable. So I have to just keep a little bit of care of which one I am causing as a basic variable. Although for that u, I may have a very large value of del f. So this one is the largest, so this one goes as a basic. But I will not simply take it as basic because I know that it has to be 0. Because for the corresponding equation, the g is not 0. So that's that little check you need to have. So if not that, then you go to the next highest del FQ and make that basic. So if you just keep this, you are able to handle that kind of nonlinearity. Okay, so it's a little special thing that you do. So looks like the quadratic programming problem I can solve by getting the Kuntakar conditions, which is almost linear, and by calling a linear programming software, which works so nicely, you see. So then quadratic programming problem can also be solved nicely. So that's the whole idea here. Okay, so here is an example of that. Quadratic programming. You see the maximum power of x1 or x2 is 2. That means it's a quadratic objective function. Constraints are all linear. I'm showing you what's happening. First constraint is an inequality constraint. This is that line, and left side is, bottom side is feasible. But second one is a equality constraint. Anything that falls on this line is feasible. So now which part is feasible? It's all the point from here all the way to there, and I'm assuming x1 greater than 0, x2 greater than 0, right? So from here all the way there on the line, any point that falls on the line up to here is feasible. Is that clear? Now my objective function is quadratic. It seems to be elliptical with the center here, and as you go away from it this way, you are increasing the function value. Now you have to minimize. Now in this line, which point is then the minimum? Where one of the point where one of these contour lines is tangent, and it happens at that blue point. Okay, it's not that edge, it's just the blue point over here. So that's the solution to this problem graphically, we can see. So I don't know how much is this. It's slightly less than, oh, I've written here 0.46 and 1.38 here and 0.46 here. So that's the optimum, and a function value of minus 2.77. Okay, so that I know graphically. Now I'll go to the Matlab and QuadProg. Again, I'm not going to Matlab and solving it, but this is the program. This is the code. You see, X and fval, QuadProg. Now this requires you to give H, F, A, and B. Now what are these H, F, A, and B? Here is the syntax for the Matlab. That you are describing your objective function as quadratic. So it has a linear part, which is like before, f1, x1 plus f2, x2. So f is a vector that describes the linear part, and H is the Hessian matrix, evaluated at 0, 0. So that's how you get the quadratic approximation of the problem. Okay, and then constraint will be ax less than equal to b. You can also have equality constraint. Matlab has a very generic quadprog, but it's called quadprog, quadratic programming, and the linear programming is linprog. Okay, so now what I have to find out is for this problem what is f and h and a and b. So f for this problem, let's go back. H for this problem is the coefficients of the linear terms, which is minus 3 for x1 and minus 3 for x2. Okay, so that's why I've written here minus 3. As I said, the vector you can either give as a row vector or a column vector. So here I've given as a column vector. H has to be the Hessian matrix. So you can compute the Hessian matrix from here by doing a double derivative, getting the matrix, and put x equal to 0. When you do double derivative for quadratic, there is no x. You will get constant, and that matrix happens to be in this case 2, 1, and 1, 2. Okay, I don't know what is this coming here, but yeah. So that's this is. So and what is a? The constraints. A will be the coefficients here, 1, 1, and then that's it. There is only one inequality constraint. So a is 1, 1, and right side is b. It's 2. Sorry. So a is 1, 1. Okay, this is a trick I've used. 1, 1, and 2. Here I didn't want to use the a equivalent and b equivalent. So what I have done, I have converted the equality constraint into two inequality constraints. Okay, so I said this one would be same as saying 3x1 minus x2 greater than equal to 0, and 3x1 minus x2 is less than equal to 0. Only way that can happen is it's equal to 0. So it's a small problem, so I just did it that way. But you could use this one as a equality constraint and this one as a inequality constraint also. So one time when I'm saying less than equal to 0, my coefficient is 3 and minus 1. When I'm saying greater than equal to 0, I have to multiply by minus 1, then it will be minus 3 and plus 1. So there are two more constraints, 3 minus 1 and minus 3 plus 1. And the right hand side is 0, 0. Okay? Now if I call this, I get the result 0.4615, 1.3846, and minus 2.7 is the result. So it works. Okay? So you could solve this by also doing A and B. So let me just go back to Matlab and see if we can at least if I can show you the quadratic programming syntax here. Quadratic, okay, so I need to get back to, okay, there's a lot of things I have to do here. Wait, F1. Okay, so I'm now going to quadratic programming. Yeah, it's called quadprog. Click it. Now you see the syntax. Minimum requires is HF, where there is no constraint. Even you can just have the quadratic objective function and solve using this. AF, AB, that's the minimum needed if you have a constraint. You can also do A equality and B equality separately also. Okay, and then there are many other options, and run it. So why don't we run it? The same problem. So let me create a new one here, script. Okay, someone tell me what is the F? -3 -3. Okay, what is H? 2 1 semicolon 1 2. Then I will use now A and A inequality and equality separately. So tell me only the equality constant coefficient. 1 1. And what is B? Only for the equality constraint. Inequality constraint, sorry. Why there are two? There is only one inequality constraint. B is the right hand side. 2. Okay. And then we'll say A equivalent. What is the equality constraint? 3 minus 1. And B right hand side of that? 0. Okay. Now I'll use the syntax here, X FV equal to, doesn't matter, quadprog. I think the syntax was, here it comes up as a help. H F A B A equality B equality, right? Let me not put the semicolon here, and I'm going to run. It will ask me for, in the same directory, I'm going to say quad prog 2 or 1 dot m. Save it, and it gave me the result, same result, right? It ran it, and it says here when it terminated, what did it say? Let's see. It says minimum found that satisfies the constraints. Optimization completed because the objective function is non-decreasing in feasible directions to within the default value of the optimality tolerance. So it has some tolerances and all that. So it is successful. Stopping criteria details you can find by clicking it here, and then x values are given here and the function value is given here. Okay, so either you can solve it the way I have done it here with just A and B, or you could do it with inequality equality separate. Okay, so now I go back to my slide again. All right, now we've got linear programming algorithm, we've got quadratic programming algorithm. Now what about any arbitrary nonlinear programming? As I said, that you can approximate the objective function of any arbitrary nonlinear objective function as a quadratic function, and all the constraints as a linear approximation by Taylor series, right? You could do that. Then you got a QP, quadratic programming problem. You can call this method QP and get the result. At that point, you can again approximate the problem as another QP, and you can keep doing it. So this is called the sequential quadratic programming. Like I mentioned, sequential linear programming, which is not so popular really. Sequential quadratic programming is very popular because quadratic function is much more generic than linear, right? It can capture the optima very nicely than a linear function. So here I'm showing you how to do the quadratic approximation for objective function and linear for the constraints, but all these are coded in a software called fminCon in Matlab. I'm not going to demonstrate you that because it's a bit complex to do, but here I may have some slides to show you how to do that. So SQP using Matlab. So basically it's a sequential way you are calling quadprog. You can give your function this way. This says that x is the variable and you are providing the function, mathematical function. This is the one we are minimizing. There is no inequality constraint in this. So let's say I'm just going to, this is a quadratic function, right? X to the power 4, because there is a square, there is a square. So it's not a quadratic problem. But let's say I don't add any constraint to start with. So there is no constraint of any kind. I am giving an initial starting point x naught as 1 comma 1. I'm starting from there, and I'm specifying the lower bound of that is 0 0. Upper bound I didn't give anything. So the problem that I've really trying to solve here is this: minimize for both x1 and x2 x1 square plus x2 minus 11. That is the contour problem that I was showing you all the time. I was showing you yesterday. Same function here. Square subject to both x1 and x2 is greater than equal to 0. There is nothing else. And so this is an unconstrained problem in some sense, except that there is a lower bound. And I'm starting with x naught equal to 1 comma 1. Okay, so that's the problem I'm solving. So here, to use SQP, you have to go to the option, and there is a command called optimization options. Choose fmin_con, display every iteration of how it's doing, and choose the algorithm as SQP. Okay, if you do that, this is the syntax x, and you can also put x comma fb, the function value it will give. This function that you have described first, it's going to minimize starting with x naught. A is nothing. So there is nothing means if you want to give a null vector, you just put two square brackets close to each other. So A is null, B is null, A eq null is B eq null, LB is the 0 0, upper bound is null. Now put the constraint is also null. Okay, constraint function I didn't tell you. I have to show you how the constraint function is before I do that. And then at the last you put the option, because this tells you what you want to do. The constraint function, oh sorry, I've added the constraints. So this is not the only problem in this. So I could have solved without the constraint, but I have added here x1 minus 5 square plus x2 square minus 26 less than equal to 0. Here it assumes less than 4x1 plus x2 minus 20 less than equal to 0. So these are the two constraints I am using, and this is exactly the problem. You remember where the optima goes? So we had this function sort of like this, and here is the one constraint, and the other constraint is like this, and the way I have done that is less than, right? So this is still my optima, 3 comma 2, because these constraints are inactive. So this is 3 and 2 is still my optima. Okay, so you create another file called constraint.m, and you write this. So that way you get the constraints. I'm going back to the previous slide, and I'm putting that as a constraint here. I could also do the same thing. I could open an objective file as well and put it the same way. So here you give your objective function, here you give your constraint functions, and then here starting point. If you have any linear equality or inequality, you can give it. These are all linear inequality and linear equality. If you don't have, I could have given this linear one there, but I just decided to do everything under constraint, and lower bound and upper bound of the variable. Okay, so it's very generic. And then when I run it, this is the result I get, that every iteration is printing out how much function values it's computing, how many new function values it has computed, and how the fx is going down to its optima, and whether everything is feasible or not. So it's able to find right from the first iteration a feasible solution and keep maintaining the feasibility by reducing the function value to 2.5. Sorry, this is 0.25, right? Yeah, 0.25. So your x becomes 0.5, and no, what is that? It's a different problem. I have a different problem here. Okay, so we can quickly run it. Let me see if I can save it very quickly to show you. So I'm going to take everything from here, copy it, and go to Matlab. And then I open a new one, script, and put it here. Okay, and then I'm going to open another file. Okay, first I need to save this. You can save it here. Save as. So I'm in the exercise. Okay, fine. So let's call this fmin_con 1. Fine. Now I'm going to go to the slides and go to the next slide. and get the constraint function. So you see the whole process of what I am doing. And I go back to Matlab and I open another script, another file, save it there. Okay. This time I will have to put the name as constraint because this is that. So I'm going to save it here as constraint. Save. Okay. So in this directory I've got a constraint.m, which is this, and I've got a function which I'm going to be running. So I can reduce that gap. Okay. It's the same thing that I've got. Now I have to run this file. So I make clear of everything from the memory, and now I'm going to run. First it's going to ask me to save. No, it's already saved. So it has run it and gave me 3,2. Okay, that's what I thought the solution, and it has found, yeah, and it shows you with iteration what's happening. So that result I have in the book. This is for another problem. I'm sorry, cut and paste was wrong, but here is the correct result, and it shows how the function values are reducing down to 0. Actually, the function value there is 0. Now what I'm going to do, I'm going to change the sign of this constant. Can you show me this picture on the page here? So I'm going to now change the sign of this constraint, so that now the optima 3.2 that I found now is no more the minima. So the minima moves here, right? They are not showing it. Can you show me this? Yes. So now the optima will be this, right? Remember that it moved over there. If I put the sign and said this is feasible now, if that's feasible, then this 3.2 cannot be an optima anymore. So I can simply do that by going to my constraint file. Now get back, yeah, constraint file, and changing the sign of these. So what I'm going to do, put a minus sign here. Okay, when I send it, I'm calling it minus. So that's how I've changed the sign of the constraint. Now I save it, Control S. Now I go to fmincon1 and run it. See, the point goes to 0.829 and 2.933, and the function value is not 0, it's about 60.37. So these results I've shown you with the penalty function approach, right, and other. That's one way to do, but you can also do SQP, which is a nonlinear programming that makes it QP, makes sequentially lots of QPs and solve it. Okay. So somebody was asking me, is there a software that I can use? So you can go to Matlab and put your objective function like the way I've done, or you can create another file with like I've done the constant. You can say object.m, and you can put the objective function the same way with the syntax. Again, if you do fmincon here, it tells you the whole syntax. So everything is here. Fmincon. So here is the syntax, what all it can do. Okay, and again some kind of examples are there, so you can see different ways of doing it. Is that clear? So we showed you how to do linear programming, quadratic programming, and a most generic version, which is SQP with constraints, nonlinear constraint. Because now that you have a constraint.m file, you can put any constraint, any nonlinear constraint you want, and any objective function you want. It doesn't have to be structured like that. Okay, but sometimes it works, sometimes it doesn't. Sometimes it depends on the initial point you are giving. Okay, so you may have to do some trial and error with that. And it can get stuck to a local solution. All these can happen. Okay, so now I get back to the next topic. I'm still on the yesterday's lecture, but looks like I've been very ambitious with it. But that's okay. We have time. I'll now go to this one here and click this. Now, do I have the slide? Yeah. Okay. So, any question before we move to the next topic? Everything is clear? Okay, good. Now we get a bit more complex and try to solve problems where the variables are not real number. Okay, and oftentimes in practice we have that. Variables are integers. Most common thing is some variables are integers and discrete sum variables are real. So you have a mixed, they are called mixed integer programming problems. Here we are talking about integer programming, but you can also handle mixed integer programming with the concept of integer programming. Although I say integer programming, generic term is discrete programming. It need not be that variables take only integers, it can take at an interval of 0.5, 0.1, or any other sequence. Need not have been also equi-spaced. It can be anything. So it's just that you have few discrete options. Any real number is not allowed. Some examples are, what if the number of gear teeth in your gear as your design variable? You want to have some n number of gear teeth. It cannot be 32.5, right? It has to be an integer. So if you use in your algorithm, in your computations, n as a variable and n takes 32.5, you will still be able to compute the stress, you will still be able to compute other stuff, the performance and all that you have derived out of n. You can. The math doesn't prohibit you to do it, but those you know are useless, right? Those are meaningless values, because physically 32.5 has no meaning as a number of gear tooth. Yeah, so that's what I'm getting. So let's say there have got two variables only, both have to be integers. And one of the common ways people do in classical literature is they say, I'm going to assume any real value it can take, and I'll solve the optimization problem. So let's say at the end you get a value which is 23.76 and 4.12. x1 is this, x2 is this. Both have to be integer though, but you have excluded the integer restriction, solved, let's say, using SQP, and you found a penalty function, and you found this. Now you say, I'm going to round it off. Okay, he's always ahead of me, right? He always tells me what is next coming. That's very good. So what do I round it off? 23.76. I don't know whether I should go more or less. So let's take two. So one is called the floor, the other is called the seal, right? So the floor value of 23.6 is 23. The definition is the highest value smaller than the number. The highest allowable value higher than the number. That is 23. What did I say? Highest allowable value smaller than the number. 23.76, highest integer value smaller than 23.6 is 23. And seal is the opposite, the smallest allowable value larger than the number. So that is 24. Basically two side value you take. And then 4.12, if only integers are allowed, 4 and 5, right? So now you have two combinations here. You have total 4 combinations, right? So all I can do now, I can look at, compute the function value and their feasibility for all these 4 solutions, right? And see which one is best. Would that be the optima of this integer programming problem? Why not?
Out of these 4 values?
Yeah. Out of these 4 values, whichever is the highest, let's say I'm minimizing. Whichever is the smallest f and feasible, I say that is my optima. Is the statement true?
No.
Why not?
So it might be a multimodal program.
Okay, there can be some complexities, complications in the function, multimodal. When you optimize for this, you got stuck into the global. You got into the global solution, but it is changing so fast that when you approximate, these have very low value. On the other hand, if there is a local optima somewhere else with slightly worse f value, but when you approximate like this, it doesn't go too bad, then that may be the global integer solution. So you are perfectly right that this process doesn't guarantee in a multimodal scenario whether you will get the best optima. There is another problem also. There are 2 problems. The first problem is, let's say there are mixed integer programming. Now, 2 of them are integer, 1 of them is real. Let's say that, or let's say one of them integer, one of them real. So this is supposed to be integer and this is real. So you do the lower and upper value, the floor and the seal. So 23, and then you'll keep 4.12, because this you can take real. So you don't want to change it to 4 and 5. So 4.12, then you have 2 solutions, and 24 and 4.12. Now I evaluate these 2 and determine whichever is the best. Can that be the optimum? Now let's say I'm even make it simpler. I'm saying there is even unimodality. I know that the problem doesn't have multiple optima. Can one of these 2 solutions, 23 and 4.12 and 24 and 4.12, be the optima? May not. Why?
Means that there may be, it depends on the functional behavior. Maybe.
Be more specific. Okay, here, I think you're getting there. The problem is this. 4.12 for the x2 value was optimum when you had x1 23.76. When you have x1 23, 4.12 combination with it may not be the optimum. Maybe there is 4.25 is the right combination, but you don't know that. You just copied this from here, right? If you ought to find for this, now you have to keep this fixed and optimize for the whole thing and find again what. So there is another optimization you have to do. So even for a unimodal situation, this process of just rounding it off is not the right way to do. But believe me, that's how people do, even now in practice. And I can give you very simple examples like this, why you cannot find. So you spend a lot of time doing this optimization, and now you're doing something really funny, which doesn't support any of the optimization background. I don't know why they do this, okay? But that's the first issue I said, right? The second issue is even more. Let's say one of the variables here I'm talking about is a code for material, which means I have a material as a variable. So if you say material as a variable, what are we talking about? Let's say I have 10 different materials I want to choose. 5 different grades of steel, copper, aluminum, cast iron, whatever. 10 different materials I've got. So these are my values of that variable, which is the material variable. So it is something Professor Das was saying on the first day in the inauguration, that you have non-numeric variables. So this is a non-numeric variable saying material is my variable. It's a non-numeric thing. As soon as it's a material, you have few options and you have to choose one of them. Which one is optimal? So one of the ways people do, they number it. 1, 2, 3, 4, 5, 6, all the way 10. And say, now I converted the non-numeric to a numeric value. So this 1, 2. And if it's 2, it is this material. If it's 5, it is that material. Now if you use this concept where you assume everything real, what material is 2.35? We have no idea, right? Our algorithm will stop because it doesn't know what material you're talking about. So rounding off, and first of all, the assumption that you can assume it to any real number and solve breaks down in certain cases, right? So the problem has discrete variables. Your optimization to treat it as a discrete variable right from the beginning. That's the only way to solve these problems. And some of these classical methods are designed based on gradient and all these, thinking that it's all continuous. So if you have any non-continuity out of it, or some other stuff we talked about, nonlinearity, multimodality, they just try to make some fix-up to the algorithm. And this is one of the fix-up, rounding off and all that. But those fix-ups don't work very well. But there is a very good way people come, and believe me, this is the best way people solve these days. Okay, it's called the branch and bound method. It's more intelligent than this rounding off that I talked about. So let me first tell you the principle, and I will show you, because Matlab also has a code for branch and bound, so I will show you how it works. First, you assume that you can do a real approximation of the variables. So with this method, even you are excluding that material type of constraints. You cannot. Even with the branch and bound, you cannot. Simply, you just cannot do it. But there are many other problems which are not like the material type, where you can assume, like the number of teeth I said, you can assume it, but you can still compute the objective values and constraints. You can run your algorithm, but after you get the optimum, it could be meaningless, and then you try to do some fix up on it. That's exactly what it does, but in a much nicer way. Okay. So the idea is this. You've got the optimization problem, which has some variables which are non-continuous, some discrete or integer. You assume everything is real, and then you solve the problem. Let's say in this case, both x1 and x2 supposed to be integer. I've solved the problem being taking that assumption out, and I get 2 real numbers as the optimum. Okay. Now what they say, fine, you've done one optimization. Choose one of these variables. Let's say in this case I choose x1, and branch into 2 more problems. To the left side problem, I will add a constraint. I will say x1, because this is 4.56, the floor value of that is 4. I say x1 has to be less than or equal to 4. An additional constraint I put on this problem now. The original problem plus this constraint. And I solve it again assuming it's a real valued problem. Here I add the constraint x1 greater than or equal to the seal of the number, which is 5. So this constraint is added again to the original problem, and solve it. So there is a difference between the two problems. There is no common point between the two because of this constraint, right? Now the question I'm asking you is that this problem is splitted or branched into two. If I combine the whole search space, because there is a non-overlapping search space here, right? If I combine the whole search space, did I leave out any feasible solution that was here but not here in the combined space? Any feasible solution, I said. No. So every feasible solution with the integer restriction is included. So I can do that. I can split it. So I have not left out anything. If I had left out anything, then optima could have been there and the whole process will be erroneous, right? But I have not left out anything. So that's good sign. Okay, now I solve this with an additional constraints, again assuming linear, and then I get another solution. Based on the outcome, I can again split. Okay, like that I will be keep on splitting. But then it will keep on growing, right? At some point we have to stop. There are 3 stopping criteria for each of the nodes. First is, let's say this point you have come, but this solution that you've got here after optimizing with this constraint, it turned out this is an infeasible solution. So that means by adding these constraints, it's contradicting with other constraints, and there is no solution that's feasible. Is there any point for me to branch from here? No, because the node itself is infeasible. If I split this into 2 more, it'll all be infeasible. I'll not be able to get anything. So you say, okay, put a line. A line means, there's a name for it, it's called fathom or bound. Okay, bound it. No point going further from here. So bound it. So that's one criteria. Second criteria, let's say this one here. I've got an integer solution. I got both values of x1, x2 by optimizing it are integers. Is there any point for me to branch? The answer is again no. I've got what I wanted. But I'm not sure if that's the optima. But at least to this partition, I found an integer solution. So I should not again split. So that's another condition. Third one is a little tricky. Third one is this. So let's say I found an integer solution here. Let's take an example. Let's say I'm minimizing. I'm minimizing the problem, and I've got a solution here of value 10, function value 10. I'm minimizing. Okay. And now I come over here. I did not find the integer solution because this is coming from another root. So I didn't find the integer solution. Let's say the value here is 12. The optimal function value here is 12. Here it is 10, but that's an integer solution. Here it's non-integer solution. I got a value of 12, f star. Is there any point for me to move? Why not? Because 10 is better. But then with 12, if I solve it, maybe I can split into something that is better than 12. Is it possible? So if I have a node, that means I have a feasible space of what the problem where the best solution is 12, right? Now I have split into 2. So none of them I'll have less than 12. I can have one of them maybe equal to 12, but not less than 12. So there is no point for me to go any further because I already have a better solution. Okay? So that means you have to start from the top, level 1, level 2, level 3 like that, and you have to keep recording the integer solutions you're finding. And the better one you have to keep recording. And as soon as you have a situation where you have a value that is a non-integer solution and it's worse than your current best feasible solution, you don't just branch there. So these are the 3 ways you can fathom it, and you keep diversifying otherwise. At some point, every open node will be blocked, will be bounded, then you stop and declare the current best integer solution. So that's the whole branch and bound method. There is a version called branch and cut. It does little better than this, but it's very similar principles, so I'm not talking to you about that. So one thing that left is, when I have 2 or more variables to split, which one shall I split to? Shall I take x1 or x2 or which one? Oh, there is no agreement on that. There are several things people use. Sometimes they say, which variable is more important to you? So you have a diameter, you have a length or thickness, you have some idea, being the practitioner, being knowledgeable about the problem, you know this variable is more important to me than that. So the most important variable is split at first. Okay? If you don't have any such knowledge, you can use a principle like which one is the higher value, because that if I control, maybe my function value gets set quickly. So you can use that, or you can just use an arbitrary one at random. You can choose anything. So there is no agreement. It usually comes with experience of people solving different kinds of problems. Okay, so here's the whole method I've already talked about. Let's take an example. You could do this with linear programming, you could do it with quadratic programming, you could do it nonlinear programming. Any programming has an integer restriction, you can use it. Only thing is, this optimization that you're doing, if the original problem is linear, all these you'll be using linear programming. If the original was nonlinear, you have to use nonlinear programming. That's it.
But sir, computationally won't it be very expensive?
Yeah,
comparing
it is very, very expensive. It's called an exponential algorithm because as the number of variables increase, the number of branching you have to do exponentially goes up. And I will show you some results. We have done that on a very big problem like the billion variable problem I've been keep referring. We tried to solve. It's an integer programming problem actually. So we tried to solve using this. I was surprised that this method could even solve a 1,000 variable problem. But when you went to 2,000 variable problem, it could not solve. And the industry needed me to solve a 50,000 variable problem, 50,000 integer variable. So this was not the solution. So we had to develop our own method for solving that. We'll talk about that later. Okay, so here's a 2 variable problem, but nonlinear, 2 constraints. We just solved that problem. 3, 2 is the optima. But I changed it. No, this 11 I changed to 9. So now 3, 2 is not the solution actually. So see what happens. When I first, so this is an additional thing now. So up to here you are familiar, right? Now I said x1, x2 are integers. As soon as you see that, you know that it's an integer programming problem. Okay. So now first I take that out and solve this problem, and we can actually go to SQP right now and just modify my file 11 to 9 and solve it, and we'll get this result. Okay. Now you see both of them are non-integer. So, but the f value is 0. So what I do, I branch into 2 problems. One is I am adding x1 less than equal to 2. So I've decided to go on x1 less than equal to 2 and x1 greater than equal to 3. So here is my overall problem. I had this optima. I split into 2 problems. NLP2 now is here and NLP3 now is here. Now I'm going to be solving these 2. And when I get a result here. This is NLP3 result. Okay, 2, 2.324. F value is this. And NLP, where is the NLP2 result? NLP2 result here. No, I don't have it here. Maybe it's hidden behind one of them. Okay, so there was an NLP2 solution, and then this is the NLP3 solution. So the idea is NLP2 now is splitted into 2 more problems because I had an issue with x2. x2 was not integer, so it got splitted into NLP4 and NLP5 with an additional constraint x2 less than equal to 2 and x2 greater than equal to 3. And when I solve 4, I get an integer solution. 2, 2. When I solve 5, I get an integer solution. So I will fathom them. Okay. Now NLP3 has to be split also into 2 problems. And when I solve, I get 2 integer. So everything is fathom now. Now I look at which one has the best value, and I get that. So here is the flow chart. So I want at the end, when you do the homework, you will make such a flow chart. This is how I'm started. Both are real numbered. Function value is very close to 0. I choose x1 to split, and I get NLP3. The result is 3, 1.925. So I split into 2 problems, and similarly NLP2 here split into 2 problems. Now everything is fathom because I've got an integer solution here, and this has the best result. So 3, 2 is the best value for this problem. Okay, but as I just mentioned, this can be exponential. Okay, the branch and cut, it's a fix up that you have based on certain properties of that. Again, comes from the concept of the splitting up to the floor and how much value you have. It's just computationally a little faster. So simplex method actually implements branch and cut. Most of the sophisticated methods, in fact, the intlin-prog also implements the branch and cut method. Okay, let me demonstrate to you. Okay, let me show this first here because I have all the results here. So let's say I've got a linear problem now. Minimize this, subject to 2 constraints, both linear. Okay, and here is the sketch of that problem. So in the homework, when you solve, I give you a LP problem to solve, but with integer restriction, you will be making sketches to solve the problem, not using the tabular method. Then each LP will take a lot of time for you to solve. So you can just make a sketch like this, and because they are linear, so you can determine by the sketch where is the optima. Here, The optimum is right here. We are minimizing, but that solution is not an integer solution. You see, all integers I put a blue line, but this is not falling on the integer, so it's not. Okay, so LP1 is this. It's not an integer solution. So I split into two, x1 less than equal to 7 and x1 greater than equal to 8. LP2 solution is this with this function value. LP3 solution is this. So x1 got 8, but x2 is not integer anymore. So now here is the sketch for the LP2 and LP3. These are the solutions. Now I split into LP4 and LP5, the LP2 problem. It so happens that LP4 happens to be infeasible. You see, here they have contradiction and there is no feasible solution because the original feasible was here. So there is no feasible solution. So I will bound it. I will not go any further from here. LP5, this one has a feasible solution, and unfortunately that's again a non-integer solution. So I have to split again. But look, the function value is 706. LP6 on the other hand is infeasible, and LP7 is an integer solution. So first time I got an integer solution. I have to note down its value. What's its value? Its value is 718, and I am maximizing or minimizing? Minimizing here. So since I've got 718 and LP's best value is 706, shall I terminate? No, I've got an integer solution. This one has a value 718. Okay, so that's my standard now, 718. Anything smaller I would accept, anything bigger I would not accept. Now when I'm at LP5, the best non-integer solution is 706.82. Shall I continue or not? Yes, I should continue because this is much better than 718. Maybe there is a, so when I continue, when I split LP5, I will get worse than 706, but it can be smaller than 718. So that I cannot leave that out, right? So I continue with LP5 one more time, LP8 and LP9. It so happened LP8 is again infeasible, but now I have 744 infeasible solution. Shall I continue with LP8? No, because I already have 718, right? LP9 I got a integer solution with 707. That's much better, right? If I didn't come and split LP5, I wouldn't have gotten it. So now I've got an integer solution, so I should bound it. So the final result is this one, 707. Everything got bounded, and here is the complex structure. LP1 I split it into two, then LP3 got splitted, LP2 got splitted, but one of them is infeasible. This one here, one of them is infeasible, the other one I got the integer solution. This becomes a standard at level 3. But now when I came to level 4, one of them I got integer and the other one I got an infeasible, but this value is worse than 718, so I did not continue. Okay, so this is a problem where all the three termination conditions have been applied. Okay, but fortunately in this problem every node is an LP, so I could solve it by picture, by the graph. But ideally each of these problem you have to solve using fmin_con separately. So now let's think from here on and go back to the very first class that we did. If you have an integer programming problem, that means some of the variables are integers. Let's say the problem is nonlinear, an integer. Every one of the node here is a nonlinear optimization problem, and you are doing several such. So each circle here is an optimization problem you have to solve. Okay. For each of them, you are calling, let's say, fmin_con, and what it's doing? It's doing a QP. Every point it's doing a QP approximation, and QP means call linear programming and solve it, right? And then go to the next point and then again approximate as QP. So each one there is a number of iterations. Fortunately we are using LP, but if you use penalty function instead of XQP as an option for fmin_con, what will you do? For every one of them here, you first form with a particular R a penalized function value and then solve it using steepest descent. Steepest descent requires line searches, which means golden section and bounding phase. Okay, and then update R. We are still stuck at the first problem. Okay, update R, go back to the steepest descent, go back to the golden section. Update R, go back. So once you've got that, you get this value. Now you go to the next one, again do the same thing. So you see the computations that's growing up until this point. Now this is a level where now you can go to practice and say, hey, give me a problem where you have integer restrictions, I can solve it. So, but then you should know all the things that goes behind getting the final result. So it's far from being easy, right? But once you have such a systematic way of knowing what's going on, you can comprehend. Now you can go back to the lowest part of the whole system, which is the golden section and bounding phase. If you can save time even there a little bit, think about how much time you can save overall. That's why I always tell golden section, because that's the best method. Very quickly you can narrow down your optima. Okay? But if you're doing the SQP route, it's actually using linear programming, so it's a different route. It's not using golden section and penalty function. Okay? But there are several algorithmic ways you can go. Okay, now let me introduce then how these integer solutions can be solved using Matlab. So it's called int-lin-prog. Okay, it's called Matlab int-lin-prog. Although it says lin-prog, it can actually do nonlinear problems as well. So they have the latest version. Matlab has, they didn't change the name, but they can handle nonlinear problems also. Okay, so the same problem that I just solved here, this problem, I am now coding it. C, remember the C is basically f, is the coefficient of the objective function. So let's get back to the objective function. 1, 10, right? And then the constraints are greater than equal to, so I have to multiply it by -1. So minus 66, minus 10, right hand side is minus 1430. This will be plus 82, minus 28. You understand, right? So let's see if I've done it properly. What's that? Is it minus 10? Why there is minus 10?
That's not the A is equal to A.
So I put minus sign here, right? Minus 66.
A1.
This should be 10. Oh, is that right? Oh, that's right. Yeah, 10. Now I don't know which one is correct. Okay, there may be a typing error here, but one of them is correct. And then B this, again at the minus value. Okay. Now an additional thing you have to do in the int-lin-prog is to say which of the variables are integers. So you could do mixed integer programming. You could just say one of them or all of them or few of them, right? So here you define a vector and give the indices of the variable. So first variable and second variable I've declared to be integer in this case. Okay? And then the syntax is this int-lin-prog, C, which is the f, the coefficient of the objective function, and then which are the integer variable that indexes, and then A and B as usual, the constraints. Okay? And when you run this, x value comes out to be 7,70, f val 707. So we can actually go and check whether it was 10 or 14. We can just run it. I guess you can try that as well. Okay, so let's not go there. But I want to talk about this one that you mentioned about the complexity. So here is the problem. I'm going to describe it later on when I get to the genetic algorithm part. But you see, it's a linear problem. So I'm not giving you the context of the problem right now. But if you look at mathematical definition of the problem, xi's are my variable. Xij, it's a matrix form. It's my variable. And it's multiplied by some linear term. So it's a linear objective function. There's one set of inequality constants. There are many of them. They are inequality. Again, linear. You see w times x. And there is equality constants. That's also linear. Sum of x is linear. So everything is linear here. Only problem is every x should be an integer. So if this restriction was not there, I could have called simplex method, lin-prog, and I can solve thousands, millions of variables without much difficulty. Million will take some time, but it can solve it eventually. And if it goes more than a million, then I will think of Converkar's method or other that will be much faster. Okay? But now the integer restriction makes it difficult. The only way to solve this is this branch and bound. If I have x going to 1000 variables, then there are 1000 ways you can branch and all that, right? So it gets more and more complex. Okay, so I thought, let's try a software. So IBM really is very proud of their simplex method. Every time I meet these people in conferences, they have a booth. They have about 10 people coming, lots of things that they do. Last conference I went with this problem and I said, can you solve this problem? He said, yeah, it seems like an easy problem. So I said, no, this is integer here. Okay. So yeah, we could do integer programming. All you have to do is just declare that as an integer. I said, can you solve, because I was thinking that I'm solving very large number of problems, so millions or something. So I said, can you solve a million variable problem? Their first impression is, yes, we can, because they know million variable for real valued they can do, right? I said, not real valued, integer values, variables, and million. Then they realized what I'm talking about. They said, oh, we have to touch you with our technical people. So then I got the phone number, I called them. This is, oh, that's too many, because they know branch and bound has an issue. And they says, we haven't tried, but go and take that drop-down menu and choose that option and this option. So I did, and I couldn't solve more than 1,000 variables. So I sent them back, this is the problem, can you solve it at your end, and because I really need to do this. After a week, they came back to me saying, no, they cannot solve it also. And they say, the reason is the branch and bound. So I said, which I knew that this was the problem. So there is an issue, and then eventually they come back to me saying, why do you need to solve a million variable problem? So because they cannot solve it, now they're asking, do I really need to solve it, or I'm trying to just show that simplex doesn't work? I said, no, I don't need million variable at this point, but I need 50,000. Can you solve 50,000 variables? Because that's the company needs. And they said, no, we cannot go more than few thousands. So, so there is an issue with the classical literature when you try to scale up. So all these methods are nice when you have small dimension, but as you try to go bigger dimensions, some of the fix-ups they use do not just scale up because they are exponential. So what I'm showing you here is a 1800 variable problem, that this problem. So x has 1800 elements in it. Okay, we are talking about 2 and 3 dimensions here, but we went up to 1800 here. Here is the result. Sorry, this worked. When I go to 1800, so we can go 1000, 1500. Finally, 1800 works. It went into 3342 nodes. Okay, it branched into, but it only took 1.22 seconds. I'm just showing you first the positive aspect of the algorithm, that such a large number of variable with a small time, it can give me the optimum. But when I go 200 more, okay, it went up to, so this is the result for the 2000 variable problem. This is in seconds. So we went up to 30 minutes here. 30 minutes is 1800 seconds, right? So up to 1800 seconds we stopped. At that point, the algorithm displays how many nodes it has branched to and how many nodes are still left to be solved. Open, there still can be branched. Looks like, look at this number here, it's about 37 million here. About 37 million nodes in half an hour it went to. Still trying to solve the problem. And this is the number for the red line here. About 34 or 32,704 nodes are still left to be solved, left to be fathomed. Okay, then I thought maybe another half an hour it will come down. So we even end up running 15 hours on this problem, and we look at the snapshot. These numbers have gone into billions. Okay, so it's keep on increasing. You see the trend? It's keep on increasing as you are running the number of nodes in a linear fashion, and the number of remaining nodes left is still it's catching up with this. It's also going up like that. So it is never going to solve it. It's just too much dimensions for it to split. Okay, and we are talking about going to 50,000 variables. So you can imagine how it will do. So some of these algorithms don't scale up, but the good news is if you are dealing with 500, 1000 kind of variable problem with integers, it can do very quickly. So there's something good part here, but it doesn't just scale up. Okay, you could do mix of real and discrete. Only thing is those ones that are real you have to declare as real, and those that are discrete you have to declare as int con. So to summarize, what we have done so far is that starting with the yesterday's one is we looked at most of these classical methods. They assume unimodality, excellent for convex problems. Okay. We also mentioned one method not applicable to many problems when we talked about NFL, and that sometimes kind of carry over here as well in this problem. So we see that effect, that problems where penalty function works well, maybe SQP doesn't do well, and where SQP does well, penalty function doesn't do well. So that kind of experience we have. constraint handling sensitive to penalty parameters. That's why we do in a sequential manner. Not so efficient in handling discrete and non-differentiable problems because they use some fix-ups which are not scalable. Other important thing is today's world we have parallel computers almost in every lab, right? Even some desktops are coming up with 8 core or 16 cores in them. So if you have a distributed computing environment, some of these methods you can't use, right? Because if you look at the algorithm, it's going in step by step by step format. You cannot jump to step 3 unless you have finished step 2. So even if you have parallel computers, how can you utilize it properly? So these methods needs to be rethought from a parallel computing point of view. This is what I also mentioned when I talked to you about golden section, but in general this is true for any algorithm. So if some of you want to really do research in this area of optimization algorithm development, this could be a very good topic, that taking some of the key algorithms from classical literature and coming up with a parallel version of those, which would be very, very fast. For example, golden section. If I have 8 core machine with me, how can I take golden section and convert it to a parallel golden section version so that I get the best out of the 8 cores? So what kind of algorithm there would be? So there's some thinking that's needed along those. Steepest descent, if I want to do. So there are various ways to go forward, I think, but this would be a good PhD topic. And this will be timely because when those algorithms are developed, parallel computers are not there, so they didn't have to do. But now it's a different situation, so we have to think in that way. But some of these methods are very good as a first method, just to get an idea how complex the problem is, how difficult it is. But I take it this way. When I get a problem from industry, I try to use one of these because softwares are available, easy to apply and see what result I'm getting. Sometimes they don't even give me a feasible solution. Okay, so I see what kind of, like here for example, I first tried this problem from industry which I have to solve 50,000 variables, and I see I'm stuck at 18,000, 1800. So I have a case. I have a case to say, oh, these methods cannot handle them, so I need to think of something else. That's how you graduate to some more advanced algorithms. Okay, so this can be always used as a first method, and that's where I'm going to start the genetic algorithms and population-based methods, which are more advanced, more flexible. You could do a lot of things with them, but then you go away from such structured methods. You go away from proof of any kind. But just as a last word of today's lecture, let me tell you, because I don't want to give you a wrong impression. Sometimes people say some of these genetic algorithms and population-based methods don't have any proof, right? So why shall I use them, right? If I give you an arbitrary nonlinear problem, there is no algorithm with a proof. Even these SQP or any penalty function, there is no proof for any of those methods. So when you have an arbitrary problem, any algorithm is as good or as bad as another one. So you have a free field to figure out which one is best for you. Okay? But if it's a linear or a quadratic or convex, you should not even think of using any other methods than SQP, QP, or the others where I've said there is proof. So that's the last word that I want to make of today's lecture. That many people will tell you don't use GA because they don't have any proof. You should immediately say, well, for this problem which is nonlinear, what algorithm has a proof? No algorithm has a proof. Okay? So you are at the same boat, whether you use this or that. But now there should be some advantage for you to try something else. So one of the things you do is you try some of these methods, established methods, and then show that, yeah, it is not giving me the result that I'm looking for. So you have a case. Then you can defend. Because if you're using GA in any of your theses, it's still not as mature as this. There will be somebody in the committee will ask you, why did you use GA? And you should have a solid answer like what I'm giving you, right? Here showing that the classical best method I have used and it failed. So what do? I just don't solve that industry problem. I tell them, sorry, I can't solve it. Or I try to do something else and give them some result that they can use, right? So that's a solid case. You have to make that case if you are using anything other than these classical methods. So that's the end of the classical methods that I wanted to talk about. And I took all this time to do it because you need to know these, because all these methods built up the foundation of what makes a solution optimal, what are some methods, how they work, what are the drawbacks, and I have been telling them as we are going. So from tomorrow, we'll start talking about genetic algorithms and population-based methods, and mainly point out the differences and the flexibilities that they have. Okay. All right. So in the afternoon, we will